It's only 12 miles wide, technically dead, and on December 27, 2004, it altered Earth's atmosphere from 50,000 light-years away. This is not a black hole. Black holes wait. They sit in the dark, patient and silent, dangerous only if you fall toward them. This is something else. Something that doesn't need you to come close. Something that reaches across the galaxy at the speed of light and finds you whether you're ready or not. Magnetars are the most magnetically violent objects in the known universe. A collapsed stellar core no wider than a city, spinning with a magnetic field 1 quadrillion times stronger than the refrigerator magnet holding up your grocery list, strong enough to rip atoms into needle-shaped distortions, strong enough to pull particles out of empty space itself, violating what most people assume is the baseline rule of reality, that a vacuum contains nothing. And every so often, without warning, they crack. The crust fractures, the magnetic field lines snap and reconnect, and in 1/10 of a second, a magnetar can release more energy than our sun produces in 250,000 years. When SGR 1806-20 did exactly that in 2004, satellites across Earth's orbit were blinded. Our planet's ionosphere, the protective shell that stands between us and the radiation of space, was compressed and ionized from the other side of the Milky Way. Instruments built to detect the faintest whisper of distant explosions were overwhelmed, saturated, screaming. This wasn't a near miss. This was a glancing blow from an object farther away than most stars you can name, and it still reached us. So here's the question no one really wants to ask out loud. What happens if one goes off closer? Not 50,000 light-years away, 5,550. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Chapter 1. The Cosmic Graveyard. From stellar giants to magnetic monsters. The universe has a way of taking its most beautiful things and turning them into weapons. Stars, for most of their lives, are engines of balance. Gravity pulls inward, fusion pushes outward, and the two forces sit in a delicate equilibrium that can last millions or even billions of years. The star shines, it heats planets, it lights up nebulae. It does exactly what a star is supposed to do, which is burn hydrogen into helium and look pretty doing it, and then the fuel runs out. What happens next depends entirely on how much mass the star started with. If you're a small star, something around the mass of our sun or lighter, you die quietly. You puff off your outer layers, leave behind a hot white dwarf core, and fade into the background like a retired accountant moving to Florida. No drama, no mess. The universe barely notices. But if you're big, if you started your life with 8 times the mass of the sun or more, your death is not quiet. Your death is not gentle. Your death is the kind of event that sends shockwaves across entire galaxies and seeds the cosmos with the raw material for planets, oceans, and eventually life itself. You die as a supernova, and what you leave behind is stranger than anything your long, stable life ever hinted at. Let's start with the life cycle, because that's where the strangeness begins. A massive star, anything in the range of roughly 8 to 25 solar masses, spends its youth the same way smaller stars do. It fuses hydrogen into helium in its core, balancing gravity with the outward pressure of nuclear fusion. This is the main sequence, the long, boring stretch where stars do their job without complaint. But a massive star burns through its hydrogen much faster than a smaller one. More mass means more gravitational pressure, which means higher core temperatures, which means fusion runs at a furious pace. A star with 10 times the Sun's mass might only spend 10 or 20 million years on the main sequence. Our Sun, by comparison, has been doing it for 4.5 billion years and still has another 5 billion to go. When the hydrogen in the core finally runs out, a massive star doesn't stop. It can't. The core contracts under gravity, heats up, and ignites helium fusion. Helium fuses into carbon and oxygen. The core contracts again. Carbon fuses into neon, magnesium, sodium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur, then silicon into iron. Each stage burns hotter and faster than the last. Hydrogen fusion lasts millions of years. Helium fusion lasts hundreds of thousands. Carbon fusion lasts a few hundred years. Silicon fusion, the final stage, lasts about 1 day. 1 day. That's how long a massive star has left to live once it starts fusing silicon in its core. And then it hits iron and the game ends. Iron is the most stable nucleus in the periodic table. Fusing iron doesn't release energy. It consumes energy, which means that the moment a massive star starts producing iron in its core, it loses the only thing that was holding it up. The outward pressure from fusion stops. Gravity, which has been waiting patiently for billions of years, wins. The core collapses, not slowly, not gradually. In less than a second, the entire inner core of the star, a region the size of Earth containing more than 1 solar mass of matter, collapses inward and compresses itself into a ball roughly 12 to 20 kilometers across. 12 kilometers, that's the distance from downtown to the suburbs in a mid-sized city. You could drive across it in 10 minutes if traffic was light. Inside that 12-kilometer sphere is a mass greater than the Sun. The collapse happens so fast that the outer layers of the star don't have time to react. They're still falling inward, still accelerating toward the core, when the core itself rebounds. The infalling matter slams into the now rigid core like a freight train hitting a wall, and the rebound sends a shockwave tearing back outward through the star. That shockwave is the supernova, the explosion that rips the star apart, flings its outer layers into space at a significant fraction of the speed of light, and for a brief moment outshines every other star in the galaxy combined. And at the center, quiet now, untouched by the chaos it just created, sits the core, a neutron star. The name is almost too simple for what it describes. A neutron star is not a star in any sense we usually mean. It doesn't shine by fusion. It doesn't burn fuel. It doesn't have layers of hydrogen and helium wrapped around a core. It is the core, compressed to a density so extreme that the atoms themselves have been crushed out of existence. Under normal conditions, atoms are mostly empty space. The nucleus sits at the center, tiny and dense, while electrons orbit far outside in probabilistic clouds. The distance between the nucleus and the electron shell is, relatively speaking, enormous. If you scaled an atom up so that the nucleus was the size of a marble, the electron cloud would extend out past a football field. In a neutron star, that space is gone. The gravitational pressure is so intense that electrons are forced into the nucleus, where they combine with protons to form neutrons. The result is a substance that has no analog anywhere else in the universe. No empty space, no atomic structure. Just neutrons packed together as tightly as the laws of physics allow, held up only by something called neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state. The density is almost impossible to describe in terms that make intuitive sense. A teaspoon of neutron star material would weigh, depending on whose estimate you trust, somewhere between 100 million tons and several billion tons. A teaspoon, the kind you use to stir coffee, If you could somehow scoop out a tablespoon of that material and drop it on Earth, it would punch straight through the planet like a bullet through paper, not because it's moving fast, but because nothing on Earth is dense enough or strong enough to stop it. The boundary that determines whether a collapsing stellar core becomes a neutron star or something else is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in the 1930s while on a ship from India to England. He was 19 years old at the time. The Chandrasekhar limit sits at about 1.4 solar masses. Below that mass, a stellar core can hold itself up as a white dwarf, supported by electron degeneracy pressure. Above that mass, electron degeneracy fails and the core collapses further. If the collapsing core weighs more than about 1.4 solar masses, but less than roughly 2 to 3 solar masses, it becomes a neutron star. If it weighs more than that, not even neutron degeneracy pressure can hold it up, and the collapse continues all the way down into a black hole. Most neutron stars end up weighing somewhere between 1.4 and 2 solar masses. That's the sweet spot where the physics allows them to exist. Pack in more mass and you get a black hole. Start with less mass and you never collapse far enough in the first place. But mass isn't the only thing that survives the collapse. Rotation survives too. Stars rotate. Slowly, usually. Our sun takes about 25 days to complete one rotation at its equator. A massive star before it dies might take a few days or a few weeks, nothing remarkable. But when the core collapses, the rotation speeds up dramatically because of conservation of angular momentum. Think of an ice skater pulling in her arms during a spin. As her arms come in, her rotation speeds up. The core of a massive star does the same thing, except instead of arms, it's pulling in a region the size of Earth and compressing it into a ball 12 kilometers wide. The spin-up is ferocious. Newly born neutron stars can rotate hundreds of times per second. Some have been observed spinning at more than 700 rotations per second. 700. The entire 12-kilometer object whipping around faster than a blender blade. And here's where things split. Most neutron stars, once they're born, settle into a relatively predictable life. They spin. They emit beams of radiation from their magnetic poles. If those beams sweep across Earth, we see them as pulsars, cosmic lighthouses ticking away with clockwork precision. They're strange, yes. They're dense beyond comprehension, yes. But they follow rules. They behave. A small number of neutron stars, though, are born different. Or maybe they're born under slightly different conditions. Maybe the rotation was faster. Maybe the magnetic field in the collapsing core was aligned just right. Maybe the convection currents in the newborn neutron star's outer layers amplified the field through a dynamo process we don't fully understand yet. Whatever the reason, these neutron stars end up with magnetic fields that are not just strong, not just unusually strong, 1,000 times stronger than a normal neutron star, and 1 quadrillion times stronger than the magnetic field of Earth. These are magnetars. The word itself sounds like something out of science fiction, magnetar, a portmanteau of magnet and star, coined in 1992 by physicists Robert Duncan and Christopher Thompson to describe a theoretical object they believed could explain certain observed bursts of X-rays and gamma rays coming from deep space. At the time, the idea was controversial. A magnetic field that's strong shouldn't be stable. It should decay. It should tear the star apart. It should do a lot of things that would prevent it from existing in the first place. Except the bursts kept coming. And the more astronomers looked, the more evidence piled up that these objects were real. A magnetar is, in the simplest terms, a neutron star with a magnetic field so powerful that it dominates everything about the object's behavior. The field is strong enough to warp the shape of atoms. strong enough to make empty space itself slightly birefringent, splitting light into two polarizations. Strong enough that in theory, if you got within about 1,000 kilometers of one, the magnetic forces would disrupt the electrical activity in your neurons before anything else killed you. You wouldn't be crushed by gravity first. You wouldn't be vaporized by radiation first. The magnetic field would interfere with the molecular bonds in your body, and you would simply stop being a coherent structure. That is not a normal way to die. That is not a normal object. A typical neutron star's magnetic field clocks in at around 10 to the 11th or 10 to the 12th Gauss. That's already absurdly strong. Earth's magnetic field is about half a Gauss. A hospital MRI machine runs at around 10,000 Gauss. A neutron star's field is 100 million to 1 billion times stronger than that. And a magnetar's field is 1,000 times stronger than a neutron star's. We're talking about 10 to the 15th Gauss, a number so large that writing it out in full takes 15 zeros. The strongest magnetic fields ever created in a laboratory, fields that exist for milliseconds inside experimental fusion reactors or particle accelerators, don't even come close. The strongest sustained magnetic field humanity has ever produced is around 45 Tesla, which translates to about 450,000 Gauss. A magnetar's field is more than 2 billion times stronger than that. And this field doesn't just sit there. It's not static. It's dynamic. It twists. It snaps. It reconfigures itself in violent spasms that release torrents of energy in the form of X-rays and gamma rays. These events, called magnetar flares, are some of the most powerful electromagnetic explosions in the known universe outside of supernovae and gamma ray bursts. The largest flare ever recorded happened on December 27, 2004. A magnetar called SGR 1806-20, sitting about 50,000 light-years away on the far side of the Milky Way, erupted. In 1/10 of a second, it released more energy than the Sun produces in 100,000 years. 1/10 of a second, 100,000 years of solar output. The burst was so intense that it briefly ionized part of Earth's upper atmosphere, disrupting radio communication and affecting satellites. From 50,000 light-years away, if that flare had happened from a magnetar just 10 light-years away, it would have stripped a significant portion of Earth's ozone layer and likely caused a mass extinction event. The nearest known magnetar, for the record, is about 9,000 light-years away, far enough that we're probably safe, probably. But the thing about magnetars is that we don't know how many of them there are. In the Milky Way, we've confirmed about 30, but that's just the active ones, the ones currently flaring or emitting detectable X-rays. Magnetars don't stay active forever. The magnetic field decays over time, and the star quiets down. Some estimates suggest there could be tens of millions of dead or dormant magnetars scattered throughout the galaxy, invisible to our instruments, leftovers from supernovae that happened millions or billions of years ago. We only notice them when they wake up, and we have no reliable way to predict when that will happen. So here's where we are. Massive stars die in supernova explosions. Their cores collapse into neutron stars, objects 12 kilometers wide with the mass of the Sun compressed into a space you could fit inside a small city. A small number of those neutron stars, under conditions we still don't fully understand, are born with magnetic fields strong enough to bend the rules of physics in their immediate vicinity. These magnetars rotate, though often more slowly than normal neutron stars. Many spin once every few seconds, rather than hundreds of times per second, possibly because the intense magnetic field acts as a brake, siphoning off rotational energy over time. They flare unpredictably, releasing bursts of radiation that can be detected across the galaxy. And they represent, in ways we're only beginning to understand, one of the most extreme and dangerous classes of objects the universe is capable of producing. Black holes get all the press. They're the objects everyone knows, the cosmic monsters that swallow light and warp space-time into knots. And yes, they're dangerous. Get too close to the event horizon and you're gone, stretched into a strand of atoms and pulled into a region of space where the laws of physics break down completely. But a black hole, once you're outside its immediate gravitational grip, is actually pretty predictable. It pulls. That's what it does. It doesn't flare. It doesn't emit bursts of radiation on a whim. It doesn't reach out across tens of thousands of light years and scramble your planet's atmosphere. A magnetar does. A magnetar is what happens when the universe runs out of reasonable options and decides to double down on absurdity. We've established what neutron stars are. The 12-kilometer corpses of massive stars, crushed down to densities that would make a teaspoon of their material weigh somewhere in the neighborhood of several 100 million tons. Objects where gravity is so intense that atoms themselves have been dismantled, leaving behind a soup of neutrons packed together like sardines in a can that's been welded shut and thrown into a hydraulic press. That's a normal neutron star. Strange, yes. Extreme, absolutely. But predictable. They spin. They emit beams of radiation. Some of them we see as pulsars. Those cosmic lighthouses ticking away with the kind of regularity that would make a Swiss watchmaker weep with envy. They follow rules. They behave themselves. Magnetars are what happen when neutron stars stop following rules. The defining feature, the thing that separates a magnetar from every other kind of neutron star, is the magnetic field. Not just a strong magnetic field, the strongest magnetic field that exists anywhere in the observable universe outside of maybe the first few microseconds after the Big Bang. Let's put a number on it because numbers are the only way to even begin talking about this. A magnetar's magnetic field strength clocks in at around 10 to the 15th Gauss. That's a 1 followed by 15 zeros. Written out in full, it's 1 quadrillion Gauss. If you prefer the metric unit, it's about 1 billion Tesla. Now, those numbers don't mean anything to most people because we don't walk around with an intuitive sense of what a Gauss is. So let's build some context. Earth has a magnetic field. You've seen it in action if you've ever used a compass. That field, the one that shields us from solar radiation and lets migratory birds navigate across continents, measures about half a Gauss at the surface, 0.5 Gauss. Weak by any standard, but strong enough to do the job it needs to do. A refrigerator magnet, the kind you use to hold up grocery lists and children's drawings, clocks in at around 50 to 100 Gauss, 100 times stronger than Earth's field, concentrated into a small chunk of ferrite or neodymium. An MRI machine, the kind used in hospitals to image soft tissue inside the human body, runs at about 10,000 Gauss. That's strong enough that you have to remove all metal from your body before you go anywhere near it. Wedding rings, belt buckles, underwire bras, anything ferromagnetic. Because if you don't, the machine will yank it off you with enough force to cause serious injury. The most powerful sustained magnetic field ever created in a laboratory, produced by a device called the hybrid magnet at the National High Magnetic Field Laboratory in Florida, reaches about 45 Tesla. That translates to 450,000 Gauss. To achieve that, you need superconducting magnets, massive cooling systems, and enough electrical power to run a small town. And you can only sustain that field in a tiny volume, a space about the size of a soda can, for short periods of time. A magnetar's field is 2 billion times stronger than that. 2 billion, not 2 times, not 2,000 times, 2 billion. To put it another way, if you took every MRI machine on Earth, lined them up, turned them all on at the same time, and somehow added their fields together, you still wouldn't come close, not even in the same ballpark, not even in the same galaxy of comparison. A magnetar's magnetic field is so strong that it does things magnetic fields are not supposed to be able to do. It warps the shape of atoms, stretching them into elongated needles aligned with the field lines. It makes empty space itself behave strangely, a phenomenon called vacuum birefringence, where the quantum foam that underlies reality gets polarized by the field and light passing through it, splits into two separate beams with different polarizations. This is not theoretical. This is not speculative. This is something that actually happens, confirmed by observations from X-ray telescopes watching magnetars across the galaxy. The field is strong enough that if you were somehow standing 1,000 kilometers away from a magnetar, which you wouldn't be because you'd be dead from a dozen other things first. But let's pretend the magnetic forces acting on your body would interfere with the electromagnetic bonds holding your molecules together. Your atoms would stop talking to each other properly. The electrons in your nervous system, the ones that carry signals from your brain to your muscles, would get scrambled by the external field, and you would stop functioning as a coherent biological organism. You wouldn't be ripped apart. You wouldn't be crushed. You would just stop working. The magnetic field would turn you off the way you turn off a light switch, from 1,000 kilometers away. For context, the International Space Station orbits about 400 kilometers above Earth's surface. A magnetar could kill you from more than twice that distance without even trying, not through gravity, not through radiation, just through the passive existence of its magnetic field sitting there, doing what magnetic fields do. And here's the thing. A magnetar is still a neutron star. It still has all the properties that make neutron stars terrifying in the first place. The crushing gravity, the surface temperature that can reach millions of degrees, the rotation rate that can spin the entire object dozens or even hundreds of times per second, the beams of X-rays and gamma rays spraying out from the magnetic poles, all of that is still there. The magnetic field is just an additional layer of danger stacked on top of everything else. So how does a neutron star end up with a magnetic field this strong? That's the question that kept physicists awake at night for decades after the first Magnetar candidates were discovered in the late 1980s and early 1990s. Because by all rights, a field that strong shouldn't be stable, it should decay. It should tear the star apart. It should do something other than just sit there, persisting for thousands or tens of thousands of years. The answer, or at least the best answer we have right now, is called the magnetohydrodynamic dynamo model. The name is a mouthful, but the idea is surprisingly elegant. Start with a massive star at the moment of core collapse. The core is falling inward, compressing, heating up. It's a chaotic mess of protons, electrons, neutrons, all getting crushed together under gravitational forces that would make a black hole jealous. In the span of about 1 second, the core goes from the size of Earth to the size of a city, and the density goes from something like lead to something like an atomic nucleus. During that collapse, two things happen. First, the rotation rate skyrockets. Conservation of angular momentum means that as the core shrinks, it spins faster, much faster. A core that was rotating once every few hours before collapse can end up rotating hundreds of times per second after. Think of the ice skater pulling in her arms, except the ice skater is a stellar core with a mass greater than the sun. Second, the collapse doesn't happen smoothly. It's not a gentle, uniform compression. It's violent. There are convection currents, turbulent flows of matter swirling around inside the newborn neutron star. Hot material rises, cool material sinks. Everything is churning in a chaotic dance driven by the enormous temperature gradients and the energy being released by the collapse itself. Now add a magnetic field to that picture. Every star has a magnetic field. The Sun has one. Massive stars have them too, though usually not particularly strong ones by neutron star standards. But when the core collapses, the magnetic field doesn't just disappear. It gets compressed along with everything else. And because magnetic field lines are frozen into the plasma, meaning they move with the charged particles, the field gets dragged along by the convection currents and the rotation. This is where the dynamo kicks in. A dynamo, in the general sense, is any process that converts kinetic energy into magnetic energy. Earth's magnetic field is generated by a dynamo process in the molten iron core, where convection currents and the planet's rotation twist and amplify the field over time. The Sun's magnetic field is generated by a dynamo in its outer convective layer. In a newborn neutron star, the dynamo is running on steroids. You have rotation rates that are hundreds or thousands of times faster than anything happening inside Earth or the Sun. You have convection currents driven by temperature differences of millions of degrees over distances of a few kilometers. You have a seed magnetic field that's already been compressed and amplified by the collapse itself. Put all of that together and you get a feedback loop. The rotation and convection twist the magnetic field lines. The twisted field lines store energy. The energy drives more convection, which twists the field lines even further. The process runs away with itself, amplifying the magnetic field by factors of thousands or even millions in the first few seconds of the neutron star's life. The idea was first proposed in detail in the early 1990s by Robert Duncan and Christopher Thompson, two physicists working independently but arriving at similar conclusions. They showed, using magnetohydrodynamic simulations, that under the right conditions, a newborn neutron star could generate a magnetic field of 10 to the 15th Gauss, or even higher through this dynamo process. The field would be strongest in the outermost layers of the star, in a region called the crust, where the magnetic pressure would literally deform the shape of the star, making it slightly oblate, squashed like a beach ball that someone sat on. The model explained a lot. It explained why magnetars were rare. You needed specific conditions during the collapse for the dynamo to run that efficiently. Most neutron stars probably didn't meet those conditions. It explained why magnetars tended to spin more slowly than ordinary pulsars. The intense magnetic field acts as a brake, siphoning off rotational energy and converting it into electromagnetic radiation. Over time, the magnetar slows down, sometimes to rotation periods of several seconds rather than milliseconds. And it explained the flares, because a magnetic field that strong, packed into a star 12 kilometers across, is not stable. The field lines twist, they snap, they reconnect in violent bursts that release torrents of energy in the form of X-rays and gamma rays. These magnetar flares are the signature of a star whose magnetic field is literally tearing it apart from the inside. There's an elegance to the dynamo model, but also a frustration. Because while it explains how a magnetar could form in principle, it doesn't tell you exactly which neutron stars will become magnetars. The conditions during core collapse are messy and hard to model. The rotation rate depends on the progenitor star's rotation, which depends on its history of mass loss and angular momentum transfer if it was in a binary system. The strength of the seed magnetic field depends on the structure of the star's core before collapse, which depends on details of nuclear burning that are still not fully understood. In other words, the dynamo model gives you a mechanism, but it doesn't give you a prediction. You can't look at a massive star that's about to explode and say with confidence, yes, that one's going to produce a magnetar. You just have to wait for the supernova, then look at what's left, and see if it starts flaring. And that brings us to the observational side of the story. Because magnetars were not discovered through theory, they were discovered because they wouldn't shut up. The first hints came in the form of something called soft gamma repeaters, or SGRs. These were sources of brief, intense bursts of gamma rays and X-rays that repeated irregularly over time. The bursts were soft, meaning they peaked at lower energies than typical gamma-ray bursts, and they came from the same locations in the sky over and over again. That ruled out things like supernovae or colliding neutron stars, which are one-time events. For years, astronomers argued about what SGRs were. Some thought they were neutron stars in binary systems, accreting material from a companion star and releasing bursts as the material hit the surface. Others thought they might be a new class of object entirely, something no one had predicted. The breakthrough came in the late 1990s when astronomers measured the spin periods of several SGRs and found that they were rotating once every few seconds. That ruled out accretion, because accreting neutron stars spin much faster, typically hundreds of times per second, as in falling material dumps angular momentum onto the star. An SGR spinning once every 5 or 10 seconds wasn't being spun up by anything external. It was spinning down, slowing down over time as it lost energy. And the rate at which it was spinning down could be used to calculate the strength of its magnetic field. The formula is straightforward. The spin-down rate depends on the magnetic field strength and the radius of the star. Plug in the numbers, and you get a field of 10 to the 14th or 10 to the 15th Gauss, 1,000 times stronger than a normal neutron star. That was the smoking gun. SGRs weren't a new class of object. They were neutron stars with magnetic fields so intense that the stars themselves were being deformed and cracked by magnetic stresses. The bursts were starquakes, moments when the crust of the neutron star shifted suddenly under the strain of the magnetic field, releasing energy the way an earthquake releases energy when tectonic plates slip past each other. Except the energy release from a magnetar flare makes an earthquake look like a hiccup. A major earthquake on Earth releases about 10 to the 18th ergs of energy. A large magnetar flare can release 10 to the 46 ergs. That's a difference of 28 orders of magnitude, a billion times more energetic. The name Magnetar was coined shortly after this realization, and it stuck because nothing else fit. These weren't just neutron stars, they were a distinct subclass, defined entirely by their magnetic fields. Since then, astronomers have identified about 30 confirmed magnetars in the Milky Way, mostly through their X-ray emission and flare activity. A few more have been found in nearby galaxies, though they're harder to detect at those distances unless they happen to flare while we're looking. The nearest known magnetar is about 9,000 light-years away, comfortably distant, and the farthest confirmed one sits about 50,000 light-years away on the far side of the galaxy. But here's the thing. Magnetars don't stay active forever. The magnetic field decays over time, though slowly. Current estimates suggest a magnetar's field drops by about a factor of 10 every 10,000 years or so. After 100,000 years, the field is down to 10 to the 14th Gauss, still strong by neutron star standards, but no longer in the magnetar range. After 1,000,000 years, it's indistinguishable from an ordinary neutron star, and the star stops flaring. It goes quiet, which means that the 30 magnetars we've found are just the active ones, the ones currently in their flaring phase, young enough that their magnetic fields are still intense and unstable. The Milky Way is roughly 10 billion years old and has seen hundreds of millions of supernovae in that time. If even a small fraction of those supernovae produced magnetars, there could be tens of millions of dead or dormant magnetars scattered throughout the galaxy right now. Dark, silent, invisible to our telescopes, waiting. Some of them might never wake up again. The field decays, the star cools, and after a few million years, it's just another neutron star drifting through the galaxy, indistinguishable from any other. But some of them might not be done. Magnetar activity can be sporadic. A star might go quiet for decades or even centuries before suddenly flaring again as stresses in the crust build up and release. We don't have a good way to predict when that will happen, and we don't have a good way to find dormant magnetars unless they happen to be nearby and detectable through other means, like their gravitational effects on nearby stars or their occasional emission of low-level X-rays. The question of how many magnetars exist is still wide open. The number could be in the thousands or the millions. We just don't know. And that uncertainty carries with it a faint undercurrent of risk, because magnetars are not passive objects. They are active, dynamic, violent, and their violence can reach across interstellar distances. Here's the paradox that makes magnetars particularly strange. They're called dead stars. Neutron stars in general earn that label because they don't burn fuel anymore. Fusion has stopped. The nuclear reactions that powered the star for millions of years have shut down completely. The core that's left behind is inert in that sense. It's not generating energy through nuclear processes. It's just sitting there, radiating away the leftover heat from its violent birth. By that definition, a neutron star is dead. It's not alive in the way a main sequence star is alive. It's not doing anything. It's just a lump of incredibly dense matter cooling off over billions of years. Except magnetars don't act dead, not even close. They flare. They release bursts of energy that can briefly outshine entire galaxies. They emit X-rays and gamma rays at rates that rival or exceed the output of active galactic nuclei powered by supermassive black holes. They do all of this without burning a single atom of fuel, without fusing a single nucleus. So where is the energy coming from? The magnetic field. The magnetic field is the battery. When a magnetar forms, the dynamo process dumps an enormous amount of energy into the magnetic field. That energy is stored in the geometry of the field lines, twisted and tangled and stressed like a steel cable that's been wound too tight. Over time, that stored energy gets released, slowly through steady emission of X-rays as the crust adjusts to the magnetic pressure. Suddenly through flares when the field lines snap and reconnect, converting magnetic energy into kinetic energy and radiation in a fraction of a second. The total energy stored in a magnetar's magnetic field is staggering. Rough estimates put it at around 10 to the 47 ergs, comparable to the total energy output of the Sun over its entire 10 billion year lifetime. All of that energy sitting there, locked up in magnetic geometry, waiting to be released. That's what makes a magnetar so dangerous. It's not actively burning anything, not generating new energy from fusion or accretion, but it doesn't need to. It's carrying around a reservoir of energy so large that even the tiniest fraction of it, released in a single flare, can affect objects dozens of light years away. A dead star that can still kill you, a corpse with a weapon, that's a magnetar. And now that we know what they are, now that we've defined the beast and traced its origins back to the violent chaos of a collapsing stellar core, we can start asking the harder questions. How strong is that magnetic field really? What does it do to the space around the magnetar? What would happen if you got close to one? And why exactly should you be more worried about a magnetar than a black hole? Those answers are waiting, and they're worse than you think. We need to talk about what a number actually means when you scale it beyond human experience. 10 to the 15th Gauss. That's the standard figure astronomers throw around when they're describing a magnetar's magnetic field, a 1 followed by 15 zeros. a quadrillion. The number appears in papers, in press releases, in every educational material written about these objects for the past 3 decades. And every time it shows up, it sits there on the page looking perfectly reasonable, like just another measurement, another data point to file away next to the star's mass and radius and rotation period. Except it's not reasonable, not even close. That number represents a threshold beyond which the normal rules governing how matter and energy behave start to bend, and in some cases break entirely. Let's build up to it slowly, because the only way to grasp what 10 to the 15th Gauss actually means is to stack comparisons until the scale becomes unavoidable. Earth's magnetic field, the one that keeps solar wind from stripping away our atmosphere and lets compasses work, measures about half a Gauss at the surface, not half a unit of some exotic quantity, half a Gauss, 0.5. That field extends thousands of kilometers into space, wrapping the planet in an invisible shield called the magnetosphere. It's weak by almost any standard, but it's enough to deflect charged particles traveling at hundreds of kilometers per second. It does its job quietly, and we don't think about it unless we're watching the aurora or navigating by stars. A refrigerator magnet, that little chunk of ferrite or neodymium holding up your shopping list, clocks in at about 50 to 100 Gauss, 100 times stronger than Earth's field, concentrated into a thumb-sized piece of metal. You can feel its pull when you bring it close to another magnet or a steel surface. The force is tangible, measurable, strong enough to overcome gravity and hold a piece of paper against a vertical surface indefinitely. An MRI machine, the kind hospitals use to image soft tissue inside your body, operates at around 10,000 Gauss, sometimes higher. That's strong enough that the hospital staff has to screen you for metal before you enter the room. Wedding rings, belt buckles, hairpins, anything ferromagnetic, because if you walk into that room wearing a steel watch, the machine will rip it off your wrist. There are stories, apocryphal but grounded in real incidents, of maintenance workers who brought tools too close to an active MRI and watched them fly across the room like bullets. A 10,000 Gauss field doesn't ask politely, it takes. Now step up to the strongest sustained magnetic field humanity has ever produced in a controlled setting. The hybrid magnet at the National High Magnetic Field Laboratory in Tallahassee, Florida, can generate about 45 Tesla, which translates to 450,000 Gauss. Achieving that requires a combination of superconducting magnets and resistive electromagnets, all cooled to near absolute zero, all drawing enough electrical power to light up a small town. The field exists in a bore about the size of a soda can, and even then it can only be sustained for limited periods because the forces involved are trying to tear the apparatus apart. The magnets themselves have to be reinforced with steel and titanium because the magnetic pressure, yes, pressure, is intense enough to crush ordinary materials. 450,000 Gauss. That's the upper limit of what human engineering can do with unlimited funding, decades of research, and a building full of cooling systems and power generators. A Magnetar's field is 2 billion times stronger than that. 2 billion. Not 2, not 2,000. 2 billion. The kind of number that stops meaning anything because we don't have intuitive reference points for it. You can say it out loud, you can write it down, you can do the math, but you can't picture it because there's nothing in your everyday experience that scales like that. The difference between $1 and $2 billion is the difference between buying a candy bar and having more money than most small nations. 10 to the 15th Gauss, 1 quadrillion Gauss, a magnetic field so strong that it stops being just a field and starts being a physical presence, an entity that dominates everything in its vicinity. Gravity, nuclear forces, the structure of atoms, the behavior of empty space itself, all of it bends to the magnetic field. The field becomes the defining feature of the environment, the thing that dictates what can and cannot exist within its reach. And this is where we cross into territory that most physics textbooks don't bother covering, because the conditions are so extreme they only exist in a handful of places in the entire universe. Let's start with atoms. Ordinary atoms, the kind that make up your body, this planet, the air you're breathing right now. An atom, in the simplest model, is a nucleus surrounded by a cloud of electrons. The nucleus sits at the center, tiny and dense, made of protons and neutrons held together by the strong nuclear force. The electrons orbit, though orbit is the wrong word. They exist in probabilistic clouds, regions where they're likely to be found, distributed in shells and subshells governed by quantum mechanics. The shape of those clouds, the structure of the atom, is determined by the electromagnetic force, specifically by the attraction between the positively charged nucleus and the negatively charged electrons. The electrons want to fall into the nucleus, but quantum mechanics won't let them. They're stuck in these defined energy levels, and the result is an atom with a certain size and shape. A hydrogen atom is roughly 1 angstrom across. That's 1/10,000,000th of a meter. Tiny, but definite. Now put that atom in a magnetic field. A weak field, like Earth's, does almost nothing. The electrons shift slightly, their energy levels change by a minuscule amount, but the atom's overall structure stays the same. You need sensitive instruments to even detect the shift. Turn up the field. At a few thousand Gauss, the shifts become more pronounced. The electron clouds start to distort, stretching slightly along the direction of the field. At 100,000 Gauss, the distortion is significant. The atom is no longer spherical. It's starting to look more like an ellipse, elongated in one direction. At 1,000,000 Gauss, the magnetic force becomes comparable to the electromagnetic force holding the atom together. The electrons are being pulled in 2 directions at once. The atom is under strain, and its structure reflects that. The energy levels split, the spectral lines shift, and if you're a spectroscopist trying to identify elements based on their light, you're going to have a hard time because nothing looks the way it should. At 10 million Gauss, the magnetic force wins. The atom's structure is no longer dominated by the electromagnetic attraction between the nucleus and electrons. It's dominated by the magnetic field. The electron clouds collapse into thin needles aligned with the field lines. The atom stops being roughly spherical and becomes elongated, stretched, compressed perpendicular to the field and extended parallel to it. Chemists call this regime the strong field limit, and it's the point where normal chemistry stops working. Molecules can't form properly because atoms can't bond in their usual configurations, and we're still 6 orders of magnitude below a Magnetar's field. At 1,000,000,000 Gauss, atoms as we understand them essentially cease to exist in their normal form. The electron clouds are crushed so tightly against the nucleus that the atom is thousands of times smaller in one dimension than it would be in free space. Hydrogen, the simplest atom, gets compressed into a needle about 1/100th of an angstrom wide and 100 angstroms long. It's not a sphere anymore. It's a rod. At 10 to the 15th Gauss, even that description breaks down because the magnetic field is now so strong that it's affecting the nucleus itself, distorting the quantum states of the protons and neutrons inside. The nucleus, which under normal conditions is held together by the strong nuclear force and ignores electromagnetic effects almost entirely, starts to feel the magnetic pressure. The field is literally squeezing matter at the nuclear level. This isn't speculative. This isn't science fiction. This is what happens when you solve the equations governing quantum mechanics in the presence of an external magnetic field and crank the field strength up to magnetar levels. The math has been done. The results are published in dozens of papers, stretching back to the 1990s, when physicists first started taking magnetars seriously and asking what kind of environment their surface would create. The surface of a magnetar is not a place where matter behaves normally. It's a place where the periodic table has been rewritten. Elements don't have their usual properties. Iron doesn't look like iron. Carbon doesn't look like carbon. Everything is compressed, elongated, distorted into forms that have no analogues anywhere else in the universe. And that's just what the field does to matter. What it does to empty space is stranger. In classical physics, empty space is empty. A vacuum is a vacuum. There's nothing there, no matter, no energy, just the backdrop against which everything else happens. Quantum mechanics complicated that picture starting in the early 20th century by showing that even empty space isn't truly empty. It's filled with something called the quantum vacuum, a roiling sea of virtual particles popping in and out of existence on timescales so short that they can't be measured directly. Particle-antiparticle pairs, electrons and positrons, quarks and antiquarks, flickering into being for a fraction of a second, borrowing energy from the vacuum, then annihilating and giving it back. Under normal conditions, this quantum foam is invisible. It doesn't affect anything we can measure. The virtual particles are too short-lived and too low energy to interact with the real world in any meaningful way. For most purposes, you can ignore them and treat empty space as if it really were empty. Except in a strong magnetic field, the quantum vacuum stops being invisible. The field interacts with the virtual particles, polarizing them, stretching them, preventing some of them from annihilating as quickly as they should. The vacuum starts to behave like a material, like a medium with structure, and light passing through it gets affected. This is called vacuum birefringence. Birefringence is a property of certain crystals where light splits into two beams with different polarizations when it passes through. Calcite does this, so does quartz. You can see it with a cheap polarizing filter and a flashlight. Shine light through the crystal, and it comes out the other side split into two components, one polarized horizontally, the other vertically, traveling at slightly different speeds. In a magnetar's magnetic field, empty space does the same thing. Light passing through the vacuum near the star splits into two beams, one polarized parallel to the field, the other perpendicular. The two beams travel at slightly different speeds because they're interacting differently with the polarized quantum foam. The vacuum has become birefringent. This effect was predicted by quantum electrodynamics, the theory governing how light and matter interact, way back in the 1930s. Werner Heisenberg and Hans Euler worked out the math in 1936, long before anyone had any idea that magnetic fields this strong could exist in nature. The effect was tiny, unmeasurable in any laboratory field humans could produce, and for decades it sat in textbooks as a curiosity, a prediction that was probably true but would never be tested. Magnetars changed that. In 2017, a team of astronomers using the Very Large Telescope in Chile and ESA's XMM Newton X Ray Observatory reported the first direct observation of vacuum birefringence in the light coming from a magnetar called RxJ 1856, 5-3754. The polarization of the X-rays matched exactly what quantum electrodynamics predicted for light passing through a magnetized vacuum. The effect wasn't huge, but it was there, measurable, real. Empty space near a magnetar has structure, it has properties, it is not nothing. And if you turn the field up even higher, past 10 to the 15th Gauss, and into the regime that might exist in the most extreme magnetars or in the collapsing cores of supermassive stars, the quantum vacuum doesn't just polarize, it starts creating real particles. This is called Schwinger pair production, named after Julian Schwinger, who derived the effect in the 1950s. The idea is that if you apply a strong enough electric or magnetic field to empty space, you can yank virtual particle pairs out of the quantum foam and promote them to real particles that stick around. Instead of borrowing energy briefly and paying it back, the particles borrow energy from the field itself and become permanent. The threshold for this to happen is absurdly high by everyday standards. You need an electric field of about 10 to the 18th volts per meter, or a magnetic field in the neighborhood of 10 to the 16 Gauss or higher. That's 10 times stronger than a typical Magnetars field, which means Schwinger pair production probably isn't happening on the surface of most Magnetars, though it might be happening in the immediate vicinity of a Magnetar flare where the field can spike temporarily to even higher values. But if it is happening, if there are regions near Magnetars where the field is strong enough to rip electron-positron pairs out of the vacuum and make them real, then those regions are essentially manufacturing matter out of nothing. Not out of energy in the usual sense where you convert mass to energy or vice versa. Out of the structure of space-time itself, mediated by the quantum foam that underlies everything. That's not a normal process. That's not something that happens anywhere in the solar system or in any laboratory on Earth or in any environment humans have ever directly observed outside of maybe the first microseconds after the Big Bang. Magnetars might be one of the only places in the present-day universe where space-time is being forced to create matter simply because the electromagnetic fields are too strong for it to stay empty. At this point, it's worth stepping back and asking what we mean when we say a magnetic field is strong, because the word strong gets thrown around a lot and it's easy to lose track of what we're actually measuring. A magnetic field, in the most basic sense, is a measure of how much force a charged particle experiences when it moves through a region of space. The stronger the field, the more force. The force depends on the particle's charge, its velocity, and the orientation of the field. That's the classical picture, and it works fine for everyday magnetic fields. But when the field gets strong enough, it stops being just a force on moving charges. It becomes an energy density, a pressure, a physical presence that can do work and store energy independent of whether there are any charged particles around to feel it. Magnetic field energy scales as the square of the field strength. Double the field, and the energy density quadruples. Increase the field by a factor of 1,000, and the energy density goes up by a factor of 1,000,000. At 10 to the 15th Gauss, the energy density of the magnetic field itself is enormous. Rough estimates put it at around 10 to the 34 ergs per cubic centimeter. For comparison, the energy density of nuclear matter, the stuff inside a neutron star, is about 10 to the 36 ergs per cubic centimeter. The magnetic field is carrying an energy density that's only a factor of 100 less than the matter it's embedded in. In the strongest magnetars, where the field might reach a few times 10 to the 15th Gauss, the magnetic energy density approaches or even exceeds the gravitational binding energy of the star. That's a terrifying sentence to pass, because it means the magnetic field is storing enough energy that if it were somehow released all at once, it could theoretically blow the entire star apart. The field is holding together more energy than the star's own gravity is holding together mass. That's the regime where magnetars live. A place where the magnetic field isn't just a feature of the star, it is the star's defining characteristic. The thing that governs its shape, its stability, its behavior. And because the field is dynamic, because it's not static but constantly shifting and adjusting as the star's crust flexes under the magnetic pressure, that energy gets released in bursts, magnetar flares. A large flare can release 10 to the 46 ergs of energy in a tenth of a second. For context, the Sun produces about 10 to the 33 ergs per second. Multiply that by 100,000 years, and you get 10 to the 46 ergs. A magnetar flare releases in a fraction of a heartbeat what the Sun produces in 100 millennia. That energy doesn't come from fusion, it doesn't come from accretion, it doesn't come from matter falling into the star or being compressed or heated. It comes from the magnetic field itself, from the geometry of the field lines rearranging, snapping, reconnecting. Magnetic energy converting into kinetic energy and electromagnetic radiation in a process that's violent even by astrophysical standards. The mechanism is similar to what happens during a solar flare, except scaled up by a factor of billions. On the Sun, magnetic field lines in the corona get twisted by the rotation and convection of the layers below. Eventually, the twist becomes too much. The field lines snap, and the stored magnetic energy gets released as a burst of X-rays and a spray of charged particles. A large solar flare can release about 10 to the 32 ergs, enough to disrupt satellites and cause auroras visible from mid-latitudes. A magnetar flare releases 1,000,000 trillion times more energy than that. The flare doesn't just affect the magnetar itself. The burst of gamma rays and X-rays travels outward at the speed of light, and anything in the path gets hit. At close range, within a few light years, the radiation would be intense enough to strip away the atmosphere of any planet unlucky enough to be nearby. At longer ranges, tens of thousands of light years, the flare can still affect instruments, ionize particles in space, and leave a detectable signature in telescopes across the galaxy. The December 27, 2004 event, the largest magnetar flare ever recorded, came from a magnetar called SGR 1806-20 about 50,000 light-years away on the far side of the Milky Way. The burst was so intense that it briefly saturated the detectors on multiple satellites, ionized part of Earth's upper atmosphere, and disrupted shortwave radio communication for several minutes, from 50,000 light-years away. If that flare had come from a magnetar 10 light-years away, the radiation dose at Earth's distance would have been enough to significantly damage the ozone layer. A few light-years away, and it would have been a mass extinction event. The burst would have flooded the atmosphere with gamma rays, triggering a cascade of chemical reactions that would strip away the ozone and expose the surface to unfiltered ultraviolet light from the Sun. Photosynthesis would shut down, food chains would collapse, most complex life would die. Not from the magnetar colliding with Earth, not from the star's gravity pulling us in, just from the radiation, from the magnetic field releasing a tiny fraction of its stored energy in the form of a flare. That's what makes magnetars uniquely dangerous. A black hole, for all its strangeness, is predictable. It pulls, it bends space-time. Get too close and you fall in. But if you stay outside the event horizon and away from the accretion disk, a black hole is mostly harmless. It doesn't reach out and grab you. It doesn't emit random bursts of lethal radiation. A magnetar does. A magnetar is a gun that occasionally fires without warning, and the bullets travel at the speed of light. The nearest confirmed magnetar is about 9,000 light-years away, far enough that even a massive flare wouldn't pose a direct threat to Earth. The radiation would spread out over the intervening distance, diluting as it traveled, and by the time it reached us it would be detectable but not dangerous. We'd see a bright flash in our X-ray telescopes. Satellites might register a spike in particle flux, and that would be it. But the galaxy is old, and supernovae have been exploding for billions of years. If even a small percentage of those explosions produced magnetars, and if magnetars stay active for tens or hundreds of thousands of years before going quiet, then there are likely thousands of magnetars scattered throughout the Milky Way right now, most of them are too far away to be a concern. Some of them might be dormant, their magnetic fields decayed below the threshold where they flare regularly, and some of them might be closer than we think, hidden by dust or sitting in regions of the sky we haven't surveyed thoroughly. Magnetars are small, 12 kilometers across. They don't emit much light in the visible spectrum. If one were sitting a few thousand light-years away in a dense star field or behind a molecular cloud, we might not know it was there until it flared. And we have no way to predict when a flare will happen. The timescales are irregular. Some magnetars flare every few weeks. Others go years between events. The crust adjusts to the magnetic stress in ways that are chaotic, governed by the same kind of unpredictable stick-slip dynamics that drive earthquakes on Earth. You can measure the strain building up, but you can't say exactly when it will release. So here's where we are. Magnetars are neutron stars with magnetic fields so strong that they distort matter at the atomic level, polarize empty space, and occasionally release bursts of energy comparable to the total output of the Sun over geologic timescales. The field strength is not just large, it's dominant. It overrides every other force in the star's vicinity and imposes its own rules on how matter and energy behave. The magnetic field can crush atoms into needles. It can split light passing through empty space into two beams. It might, in the most extreme cases, be capable of yanking particles out of the quantum vacuum and making them real. And it stores enough energy that a single large flare lasting less than a second can be detected across an entire galaxy. That energy is real. It's measurable. It's sitting there, locked up in the geometry of the field lines, waiting to be released. And on December 27, 2004, one of those releases reached Earth. On December 27, 2004, at 01:15 Universal Time, something happened on the far side of the Milky Way that should have stayed on the far side of the Milky Way. A neutron star 12 kilometers wide, sitting 50,000 light-years from Earth, cracked. Its crust, already under unimaginable strain from a magnetic field strong enough to distort atoms, shifted. The magnetic field lines embedded in that crust, twisted and tangled and wound tight over thousands of years, snapped. And in 0.2 of a second, the star released more energy than our Sun will produce in 250,000 years. The gamma rays and X-rays from that explosion traveled outward in all directions at the speed of light. Most of them dissipated into empty space, spreading across the interstellar medium, ionizing atoms, heating gas, doing what high-energy radiation does when there's nothing in particular to stop it. Some of those photons, a tiny fraction of the total, happened to be aimed at a small rocky planet orbiting an unremarkable star in a quiet spiral arm 50,000 light-years away. It took 50,000 years for those photons to complete the journey. They left the Magnetar when Neanderthals still walked the Earth, when woolly mammoths grazed across Ice Age tundra, when anatomically modern humans were just beginning to spread out of Africa and figure out how to make tools that didn't break after the first use. The light traveled through the galaxy, across star-forming regions and molecular clouds, past thousands of other solar systems, crossing a distance so vast that even moving at 300,000 kilometers per second, it needed millennia to arrive. And on December 27, 2004, it hit us. 15 satellites and space probes detected the burst within milliseconds of each other. NASA's Swift satellite, designed to hunt for gamma-ray bursts, caught the initial spike. The Ramati high-energy solar spectroscopic imager, built to study solar flares, saw it and briefly thought the Sun had done something extraordinarily strange. Europe's Integral satellite registered the event and immediately flagged it as unusual. Russia's Konus wind instrument recorded the gamma-ray spectrum in exquisite detail. Even the Mars Odyssey orbiter, sitting in orbit around Mars and minding its own business, picked up the signal. Some of the detectors saturated, not damaged, saturated. The incoming flux of gamma rays was so intense that the instruments briefly maxed out their counting capacity and had to wait for the signal to drop before they could resume normal operation. It was the astronomical equivalent of pointing a camera at the sun. The sensor works fine, but the input is so bright that the image washes out into a white blob and you lose all detail. This had never happened before. Not from an object outside the solar system. The burst lasted 0.2 of a second at its peak, followed by a decaying tail of X-rays that continued for several minutes. During that initial 0.2 of a second, the Magnetar briefly became the brightest source of gamma rays in the sky. Not the brightest distant source, the brightest source, period. Brighter than the sun in gamma rays by a factor of thousands. For a fraction of a heartbeat, a dead star 50,000 light-years away outshone the nearest, most active fusion reactor we have. Astronomers who were awake and monitoring their instruments when the alert came through did not immediately understand what they were looking at. Gamma-ray bursts were known phenomena by 2004. They'd been studied for decades. The prevailing model explained them as the death throes of massive stars collapsing into black holes, or the collisions of neutron stars in binary systems. One-time events, catastrophic explosions that marked the end of something. But gamma-ray bursts don't repeat. They happen once, release an enormous amount of energy, and then the source goes dark because the source has been destroyed. You don't get a second burst from the same location because there's nothing left to burst. This signal came from SGR 1806-20, a source that had been flaring on and off since 1979, soft gamma repeater. The name itself told you it was supposed to be repeating, emitting smaller bursts every few months or years, always from the same spot. That was already strange enough to earn its own classification, but this wasn't a typical SGR burst. This was 1,000 times brighter than any previous flare from that object. 100 times brighter than the strongest Magnetar flare ever recorded up to that point. The energy release was so far outside the normal range for soft gamma repeaters that for the first few hours, some researchers genuinely wondered if they were looking at a new class of event entirely. The numbers came in over the next few days as teams around the world analyzed the data. The total energy output was approximately 10 to the 46 ergs, written out in full. That's 10 followed by 46 zeros. For comparison, a large earthquake on Earth, something in the magnitude 8 range that levels cities and reshapes coastlines, releases about 10 to the 18th ergs. The December 27th flare was 10 to the 28 times more energetic than that. 10 billion times stronger than an earthquake. The Sun, as mentioned, emits about 10 to the 33 ergs per second. Multiply that by the number of seconds in a year, roughly 31.5 million, and you get about 3 times 10 to the 40 ergs per year. Multiply by 250,000 years, and you hit 10 to the 46. The Magnetar released that much energy in 1/5 of a second. At peak output, the flare was producing more power than every other star in the Milky Way combined, all 400 billion of them. For 0.2 of a second, SGR 1806-20 was the single dominant source of high-energy radiation in the entire galaxy, outshining a collective luminosity that normally measures around 10 to the 44 ergs per second. That scale is difficult to process because we don't have everyday experiences that correspond to it. But here's one way to think about it. If you took every power plant on Earth, every coal plant, every nuclear reactor, every hydroelectric dam, every solar panel, every wind turbine, every single device humans have ever built that generates electricity, and you ran all of them at maximum capacity simultaneously, the total power output would be around 10 to the 20 ergs per second. The December 27th flare was producing 10 to the 26 times more power than that. 100 million billion times the entire electrical generating capacity of human civilization, and it came from an object the size of a city. The gamma rays didn't just light up satellites, they hit Earth's atmosphere and ionized it. The ionosphere, the layer of charged particles sitting between about 60 and 1,000 kilometers above the surface, suddenly got a lot more ionized. The incoming gamma rays slammed into atoms, knocked electrons loose, and created a temporary surge in the ionization level that compressed the lower boundary of the ionosphere downward by several kilometers. Radio operators noticed immediately. Long-distance radio communication, the kind that relies on bouncing signals off the ionosphere, stuttered. High-frequency shortwave signals, normally stable during nighttime hours when the ionosphere is more reflective, suddenly behaved as if it were daytime. The ionosphere's structure had changed enough to disrupt the propagation patterns, and for several minutes, anyone trying to send a signal across a continent or an ocean found their transmissions garbled or lost entirely. This is not normal behavior for the ionosphere. The sun can do this. A large solar flare, the kind that happens every few years during solar maximum, releases enough X-rays to ionize the dayside ionosphere and cause radio blackouts. But the December 27th event happened at night. The sun was on the other side of the planet. The ionization came from something else, something external, something that had traveled across 50,000 light-years of space and still carried enough energy to punch through the magnetosphere and rearrange the chemistry of the upper atmosphere. That distance is worth sitting with for a moment. 50,000 light-years. Light from SGR 1806-20 takes 50,000 years to reach Earth. When the flare happened, when the actual physical event occurred on the Magnetar's surface, Earth was deep in the last ice age. Homo sapiens were anatomically modern but culturally still in the early stages of development. No agriculture, no cities, no written language. Small bands of hunter-gatherers scattered across Africa and beginning to migrate into Europe and Asia. The light left the Magnetar and started its journey across the galaxy. It passed through the Sagittarius arm, crossed the interstellar medium, threaded between star clusters and nebulae, and finally arrived at a planet that had, in the intervening 50 millennia, developed agriculture, built civilizations, invented writing, gone through multiple technological revolutions, and launched instruments into space capable of detecting the very photons that had been traveling since before recorded history began. And those photons still carried enough energy to affect the planet's atmosphere. If the flare had come from a closer source, the effects would have been catastrophic. 10 light-years away, and the radiation dose at Earth's surface would have been intense enough to cause widespread biological damage. The gamma rays would have triggered a cascade of chemical reactions in the atmosphere, producing nitrogen oxides that would destroy the ozone layer. Ozone, the molecule that shields the surface from ultraviolet radiation, would be stripped away over the course of weeks or months. Without that shield, UV levels at the surface would spike. Photosynthesis in phytoplankton, the base of the oceanic food chain, would shut down, crops would fail, skin cancer rates in animals would skyrocket. The entire biosphere would be under assault from radiation it had no evolutionary defense against. A few light-years away, closer than the nearest star to our sun, and the flare would have been a civilization-ending event, not through direct impact, not through heat or shockwave, just through the gamma rays flooding the atmosphere and erasing the ozone layer in minutes. The sky wouldn't look different, the air wouldn't feel different, but within days, anyone or anything exposed to sunlight would start showing signs of severe radiation damage. Within months, most complex life on the surface would be dead. The nearest confirmed magnetar is about 9,000 light-years away, uncomfortable, but not immediately dangerous. A flare like the December 27th event from that distance would ionize the atmosphere more severely, might cause longer-lasting disruptions to radio communication, might even produce measurable increases in radiation dose at the surface, but it wouldn't be lethal, it would be noticeable. The scientific community would spend years analyzing the data. There might be a few more auroras than usual as charged particles from the flare interacted with the magnetosphere, but the biosphere would survive intact. At 50,000 light-years, the December 27th flare was a spectacle, not a threat. The radiation spread out over that vast distance, diluted by the inverse square law, and by the time it reached Earth, it had weakened enough that the primary effect was scientific curiosity rather than biological harm. Astronauts aboard the International Space Station, who were outside the protection of the atmosphere and directly exposed to the gamma rays, received a radiation dose roughly equivalent to a dental X-ray. Measurable, yes. Dangerous, no. But the event marked a turning point in how astronomers understood magnetars. Before December 27, 2004, magnetars were known, they were studied. Papers were written, models were built, but they were still somewhat abstract. Objects that existed in datasets and theoretical frameworks, but hadn't really announced themselves in a way that grabbed attention outside the specialist community. The December 27th flare changed that. It was loud, it was bright, it was undeniable, and it gave researchers something they hadn't had before, a clean, well-observed example of a magnetar flare at maximum output. The data revealed details about the magnetar's structure that no amount of modeling could have predicted. The initial burst, the 0.2 of a second spike, came from the entire surface of the star lighting up at once as the magnetic field rearranged itself. The energy release was so sudden and so intense that the star's crust physically expanded, puffing outward by a few centimeters before settling back down. That expansion launched seismic waves through the star, ringing it like a bell, and those oscillations produced the decaying tail of X-rays that followed the main burst. By analyzing the frequency of those oscillations, researchers could probe the internal structure of the neutron star. Different frequencies correspond to different modes of vibration, the way a wine glass rings at different pitches depending on how you tap it. Except instead of a glass, this was a 12-kilometer ball of neutrons with a crust made of iron nuclei packed into a crystalline lattice under pressures that would crush any known material into dust. The oscillations revealed the thickness of the crust, the density of the interior, the strength of the magnetic field at different depths. Information that would have been impossible to obtain any other way. The flare also confirmed something theoretical models had predicted but never directly observed. The magnetic field in a magnetar is not static, it's dynamic, it evolves. Over time, the field lines twist and tangle as the star's interior rotates at a slightly different rate than the crust. The mismatch builds up stress. The crust, which is solid but not infinitely strong, tries to accommodate the twisting field by flexing and deforming. Eventually, the stress exceeds the breaking strength of the crust, and the crust cracks, a starquake. The magnetic field lines, suddenly released from their confinement, snap into a lower energy configuration. The stored magnetic energy converts into radiation and kinetic energy, heating the surface and launching particles into space. The December 27th event was the largest starquake ever recorded, not the first. Magnetars had been observed flaring before. But this was the first time anyone had caught one at full strength, without the signal clipping or the instruments saturating beyond recovery. The crack that triggered the flare was probably only a few millimeters wide, a fracture in the crust, propagating at close to the speed of sound through the neutron star material, circling the entire star in less than a second, millimeters, and from that tiny localized failure of the crust, enough energy was released to light up an entire galaxy. There's a certain terror in that ratio. The scale of the input versus the scale of the output. A crack you could barely see with the naked eye. If you could somehow survive standing on the surface of a neutron star long enough to look, producing an explosion that could be detected from the other side of the Milky Way. The event also raised uncomfortable questions about how often this kind of thing happens. Magnetars are rare, but they're not unique. There are about 30 confirmed magnetars in the Milky Way, and probably hundreds or thousands more that are dormant or too far away to detect. Each one is a potential bomb, carrying enough stored magnetic energy to produce a flare like December 27th. And while flares that large are uncommon, they're not impossible. Statistical models based on the observed rate of smaller flares suggest that a December 27th scale event might happen once every few decades or centuries per magnetar. Multiply that by the number of magnetars in the galaxy, and the odds start to look less comforting. At any given moment, somewhere in the Milky Way, a magnetar might be cracking. The light from that flare is already on its way toward us, traveling across thousands or tens of thousands of light years, and we won't know about it until the photons arrive. Most of the time, the flare will be too far away to matter. 50,000 light years is a long distance, and the inverse square law is unforgiving. A flare that would be lethal at 10 light years is merely interesting at 50,000. The galaxy is big enough that most magnetars are comfortably distant, sitting on the far side of the spiral arms, or out in the halo where the stellar density drops off and the odds of anything being nearby go to nearly zero. But not all of them. The nearest known magnetar is 9,000 light-years away. That's closer than the December 27th source by a factor of 5 or 6. A flare of the same energy from that distance would deliver roughly 25 to 36 times more radiation to Earth. Still not lethal, still not a direct threat to the biosphere, but enough to notice, enough to cause measurable effects. Enough that if it happened during a period when humans didn't have the technology to detect and understand it, it might show up in the geological or biological record as a brief, unexplained anomaly. There are hints of this in the data. Some researchers studying ice cores from Antarctica and Greenland have found thin layers with elevated levels of certain isotopes, products of cosmic ray interactions in the atmosphere that date to specific years in the past few thousand years. The isotope spikes are brief, lasting only a year or two, and they don't correspond to known solar storms or supernovae. One hypothesis is that they might be the signature of distant magnetar flares, events that ionized the atmosphere just enough to leave a trace in the ice, but not enough to cause widespread biological harm. The evidence is circumstantial. The isotope spikes could have other explanations. But the fact that they exist at all, and that the timing and magnitude roughly match what you'd expect from a moderately distant magnetar flare, is enough to make astronomers pay attention. The December 27th event also reshaped how the broader scientific community thought about extreme physics. Magnetars had been a niche topic, studied by a relatively small number of specialists working on neutron star physics and high-energy astrophysics. After 2004, they became mainstream. The flare was covered in major scientific journals. It made headlines in newspapers and science magazines. It became a case study in textbooks on stellar evolution and compact objects. Part of that shift was simply the drama of the event. A distant star cracks and the effects reach Earth. That's a good story. It's visceral. It connects the abstract world of astrophysics to something tangible, something people can relate to, even if they don't understand the underlying math. But part of it was the realization that magnetars represent a frontier of physics where our models are still incomplete. The magnetic fields are so strong that quantum electrodynamics, the theory governing how light and matter interact, starts predicting effects that have never been tested in any laboratory. The densities are so high that the equation of state for nuclear matter, the relationship between pressure and density inside a neutron star, is still uncertain. The energy scales are so extreme that a single flare can rival the output of an entire galaxy for a fraction of a second. These are not small gaps in our understanding. They're fundamental questions about how matter and energy behave under conditions that don't exist anywhere else in the present-day universe. And magnetars are one of the only natural laboratories where we can test those questions. The December 27th flare gave researchers a dataset that's still being analyzed 2 decades later. The light curves, the spectral data, the oscillation frequencies, all of it is feeding into models that are trying to pin down the details of neutron star structure, magnetic field evolution, and the mechanisms that trigger flares. And every new piece of data raises more questions. Why did this particular magnetar produce such a large flare? What was different about its magnetic field configuration? How much energy is still stored in the field, waiting to be released in future flares? And what would happen if a flare like this, or even larger, occurred from a magnetar much closer to Earth? That last question is the one that lingers, because the December 27th event, for all its intensity, was not the worst-case scenario. It was not the closest possible source. It was not the largest possible flare. It was just the largest flare we've observed so far, from a source that happened to be far enough away that it didn't pose a threat. But the galaxy is full of magnetars. Some of them are closer. Some of them might be capable of even larger flares, and we have no way to predict when the next one will happen. The December 27th event was not a local problem. That's the first thing you need to understand about what happened when SGR 1806-20 cracked its crust and sent a wave of gamma rays and X-rays screaming across the galaxy. Local, in the context of astrophysics, usually means within a few light years. The Sun is local. Alpha Centauri, our nearest stellar neighbor at 4.37 light-years away, is local. Anything within 10 or 20 light-years is effectively our neighborhood. The stars whose parallax we can measure easily, whose planets we might one day visit if we ever figure out how to build a spacecraft that doesn't take 10,000 years to cross interstellar space. SGR 1806-20 sits somewhere between 42,000 and 50,000 light-years from Earth, depending on whose distance estimate you trust. That's not local by any definition. That's on the far side of the Milky Way, past the galactic center, sitting in the Sagittarius arm, where the stellar density is higher and the star formation rate is more active than in our quiet suburban spiral arm. If you could somehow stand on a planet orbiting a star near that magnetar and look back toward Earth, the Sun would be invisible to the naked eye. You'd need a telescope just to find it. And yet on December 27th, 2004, something that happened at that distance reached across the void and physically altered Earth's magnetic field, not metaphorically, not in some abstract sense where we detected a signal and learned something new about the universe, physically. The radiation from that flare compressed the magnetosphere, the protective bubble of magnetic field lines that wraps around our planet and shields us from the solar wind. For a brief period, Earth's magnetic field responded to an event that took place 50,000 light-years away, as if that event were happening in our immediate cosmic vicinity. That should not be possible. It violates every intuition we have about how distance works in space. When you're 50,000 light-years from something, you're insulated from it. The radiation spreads out, the energy dilutes. The inverse square law, which governs how light and radiation propagate through space, says that the intensity of light drops off as 1 over the square of the distance. Double the distance, and the intensity drops to 1/4. Increase the distance by a factor of 1,000, and the intensity drops by a factor of 1,000,000. 50,000 light-years is a big number. The dilution should be enormous, and it was. The gamma rays that left SGR 1806-20 during the flare spread out over a sphere whose radius by the time it reached Earth was 50,000 light-years. The surface area of that sphere is incomprehensibly large. Most of the energy radiated into empty space, heating interstellar gas by a fraction of a degree, ionizing hydrogen atoms that had been drifting quietly for millions of years, doing absolutely nothing of consequence to anything that mattered. But the tiny fraction of that energy that happened to be aimed at Earth was still enough to light up every gamma-ray detector in orbit and compress the magnetosphere measurably. That's the terrifying part. The flare was so energetic that even after diluting across 50,000 light-years of space, even after spreading out over a sphere whose surface area is measured in square light-years, the photons that reached Earth carried enough punch to disrupt a planetary-scale magnetic field. Let's talk about how that works, because the mechanism is not intuitive and it's worth understanding in detail. A gamma ray is just a photon, a packet of electromagnetic radiation with a very short wavelength and a very high energy. Gamma rays sit at the extreme end of the electromagnetic spectrum, beyond X-rays, beyond ultraviolet, beyond anything your eyes can detect. A single gamma-ray photon carries millions of times more energy than a photon of visible light. That energy doesn't come from the photon being bigger or heavier. Photons are massless. The energy comes from the frequency. Higher frequency means more energy per photon. When a gamma-ray photon enters Earth's atmosphere, it doesn't just pass through cleanly the way visible light does, it interacts. The photon slams into an atom, usually nitrogen or oxygen, since that's what the atmosphere is mostly made of, and knocks an electron loose. The freed electron, now moving at a significant fraction of the speed of light, crashes into another atom and knocks more electrons loose. Those electrons hit more atoms. The process cascades, and within microseconds, a single gamma-ray photon has generated a shower of thousands or even millions of secondary particles, all of them charged, all of them moving fast. Charged particles moving through the atmosphere create ionization. They turn neutral atoms into ions by stripping away electrons, and ionized atoms behave differently than neutral ones. They're electrically conductive. They interact with magnetic fields. They absorb and re-radiate electromagnetic energy in ways that neutral atoms don't. Earth's magnetosphere is shaped by the balance between the planet's internal magnetic field and the pressure from the solar wind, a constant stream of charged particles flowing outward from the sun. The solar wind pushes against the magnetosphere on the day side, compressing it and stretches it out into a long tail on the night side. The boundary where the solar wind's pressure balances the magnetic field's pressure is called the magnetopause, and it sits about 10 Earth radii away on the sunward side, roughly 60,000 kilometers above the surface. Under normal conditions, the magnetopause is stable. It wobbles a bit as the solar wind fluctuates, moving inward during solar storms when the wind pressure spikes, moving outward during quiet periods when the pressure drops. But the changes are gradual, predictable, well understood. The December 27th flare was not gradual. It hit the magnetosphere like a hammer. The sudden influx of gamma rays ionized the upper atmosphere on the night side of Earth, the side facing away from the Sun, where the magnetosphere is normally stretched out into a long tail and the magnetic field lines are more spread out and less densely packed. The ionization increased the electrical conductivity of that region, which changed how the magnetosphere responded to external pressure. The magnetic field lines, which are frozen into the ionized plasma, got pushed and compressed by the sudden surge of charged particles created by the gamma-ray cascade. The effect was measurable. Magnetometers on the ground, instruments designed to measure the strength and direction of Earth's magnetic field, registered a disturbance, not a huge disturbance, not the kind of dramatic shift you'd see during a major solar storm, but a clear, unambiguous deviation from baseline that lasted for several minutes and corresponded exactly to the arrival time of the gamma-ray burst. One study, published shortly after the event, analyzed magnetometer data from multiple stations around the world and confirmed that the disturbance had a signature consistent with an external compression of the magnetosphere. The magnetic field lines on the night side of the planet were pushed inward briefly before relaxing back to their normal configuration as the ionization decayed and the atmosphere returned to equilibrium. This is not something that happens often. Solar flares do it. A large solar flare releases X-rays that ionize the dayside atmosphere and compress the magnetosphere from the sunward direction. But those events come from 93 million miles away, 8 light minutes. The Sun is right next door in cosmic terms, close enough that its radiation reaches us with minimal dilution. SGR 1806-20 did the same thing from 50,000 light-years away. That distance is 6 million times farther than the Sun. The dilution factor, according to the inverse square law, should be 36 trillion. And yet the flare was energetic enough that even after spreading out over that incomprehensible distance, it still delivered enough gamma rays to Earth's vicinity to measurably affect a planetary magnetic field. Think about what that implies. The magnetosphere is not a small structure. It extends tens of thousands of kilometers into space. Compressing it, even slightly, requires a significant input of energy. You're not just heating up a small volume of gas or ionizing a thin layer of atmosphere. You're altering the large-scale structure of a magnetic field that's strong enough to deflect the solar wind, a stream of particles that's been flowing continuously for billions of years and carries enough momentum to strip away the atmospheres of planets that don't have magnetic fields. Mars, for example, has no global magnetic field. The solar wind hits Mars directly and has been slowly eroding its atmosphere for the past few billion years. Early Mars probably had a thicker atmosphere, maybe even liquid water on the surface, but without a magnetosphere to protect it, the atmosphere got stripped away particle by particle until what's left today is a thin wisp of carbon dioxide at less than 1% of Earth's atmospheric pressure. Now imagine Mars sitting in the path of the December 27th flare. No magnetosphere to compress because there's no magnetosphere to begin with. The gamma rays would hit the thin atmosphere directly, ionize it, heat it, and blast some fraction of it into space. The effect would be temporary. Mars would lose a tiny fraction of its remaining atmosphere, not enough to matter on human timescales, but measurable if you had instruments sensitive enough to detect the change. A planet closer to SGR 1806-20 would fare worse. 10,000 light-years away, the gamma-ray flux would be 25 times stronger. 5,000 light-years, 100 times stronger. 1,000 light-years, 2,500 times stronger. At some point, you cross a threshold where the flare stops being a curiosity and starts being a threat. Estimates vary, but most models suggest that a magnetar flare comparable to the December 27th event would begin causing serious damage to Earth-like planets at distances of around 10 light-years or less. At 10 light-years, the gamma-ray dose at the surface would spike high enough to destroy a significant fraction of the ozone layer. Ozone, the molecule that absorbs ultraviolet light from the sun and prevents it from reaching the surface, would be broken apart by the cascade of secondary particles created when gamma rays slam into the upper atmosphere. Nitrogen oxides produced by the ionization would catalyze the destruction of ozone molecules faster than they could be replenished by natural processes. Without ozone, ultraviolet radiation from the star floods the surface. Photosynthesis shuts down in phytoplankton, the microscopic organisms at the base of the oceanic food chain. Crops on land suffer radiation damage. Animals exposed to direct sunlight develop skin cancers and eye damage. The biosphere doesn't collapse overnight, but it takes a hit severe enough that the effects ripple through every ecosystem on the planet. Food chains break. Species that can't adapt quickly enough go extinct. The planet recovers eventually, over thousands or tens of thousands of years, as the ozone layer rebuilds and life adjusts to the new normal. But recovery is not the same as survival. At 1 light-year, the effect would be catastrophic. The ozone layer would be gone within hours. The gamma-ray dose at the surface would be high enough to cause direct radiation damage to living tissue. Not immediately lethal. Not the kind of dose you'd get standing next to an unshielded nuclear reactor, but enough to significantly increase cancer rates and cause widespread cellular damage in organisms that don't have thick protective shells or the ability to burrow underground. And this is all assuming the planet has a magnetosphere in the first place. A strong magnetic field like Earth's provides some shielding. It doesn't stop gamma rays, which are electrically neutral and don't care about magnetic fields, but it does deflect the charged particles produced when those gamma rays interact with the atmosphere. The secondary shower of electrons and ions gets funneled along the magnetic field lines toward the poles, concentrating the damage in the auroral zones rather than spreading it evenly across the planet. A planet without a magnetosphere, like Mars or Venus, or any of the thousands of rocky exoplanets we've discovered that don't have active dynamos generating internal magnetic fields, would take the hit directly. The entire dayside atmosphere gets ionized. The entire surface gets exposed to the secondary particle shower. There's no deflection, no concentration at the poles, no mitigation, just raw exposure. The same goes for moons. Most moons in the solar system don't have magnetic fields. Earth's moon doesn't. Mars's 2 tiny moons don't. Most of Jupiter's and Saturn's moons don't, with the notable exception of Ganymede, which has a weak internal dynamo. If a magnetar flare hit one of those moons from close range, say within a few light-years, the surface would be bathed in gamma rays and the ionization would strip away any thin atmosphere the moon might have. Not that most moons have atmospheres to begin with, but the ones that do, like Titan with its thick nitrogen envelope, would lose mass. The atmosphere would heat up, expand, and bleed off into space as the gamma rays dump energy into the upper layers and push gas molecules past escape velocity. Europa, Jupiter's icy moon with the subsurface ocean that astrobiologists are so excited about, has no atmosphere and no magnetic field of its own. It's protected somewhat by Jupiter's magnetosphere, which is enormous and wraps around Europa like a shield. But if a magnetar flare hit Europa from a distance close enough to matter, the gamma rays would ionize the ice on the surface, breaking apart water molecules into hydrogen and oxygen. Some of that oxygen would escape into space. Some would get absorbed back into the ice. The net effect would be a temporary spike in the rate of atmospheric loss, minor on human timescales but potentially significant over millions of years if the flares were frequent enough. This brings us to the concept of reach, which is one of the more unsettling realizations to come out of Magnetar research over the past 2 decades. Reach, in this context, is the idea that certain astrophysical events can affect objects across distances that should, by all reasonable standards, render them harmless. A supernova has reach. A star explodes 30 light-years away, and the radiation can still damage the ozone layer of a nearby planet. The shockwave, traveling at a few thousand kilometers per second, takes 30,000 years to arrive, but when it does, it compresses the interstellar medium and triggers star formation in nearby molecular clouds. The supernova's influence extends far beyond its immediate neighborhood. A gamma-ray burst has reach. A collapsing star on the other side of the galaxy sends out a beam of gamma rays so tightly focused and so energetic that if the beam happens to be aimed at Earth, we can detect it even though the source is billions of light-years away. If a gamma-ray burst went off within a few thousand light-years of Earth and the beam pointed at us, it would be an extinction-level event. The gamma rays would strip away the ozone layer in seconds. The planet would be sterilized down to a depth of several meters below the surface. Everything on land would die. The oceans might protect some deep-sea life, but the surface biosphere would be gone. Magnetars have reach, and what makes them particularly dangerous is that their reach doesn't require a direct hit or a precisely aimed beam. A magnetar flare radiates in all directions. It's not a focused jet like a gamma-ray burst. It's an omnidirectional explosion of gamma rays and X-rays spreading out from the star's surface like a balloon inflating. That means anything within a certain radius gets hit. No aiming required, no lucky alignment of geometry. The December 27th flare demonstrated that reach at 50,000 light-years, most of the energy dissipated into empty space, the vast majority of it heated gas clouds and ionized atoms that no one will ever care about. But the fraction that reached Earth was enough to compress the magnetosphere and disrupt radio communication. That's reach. That's a dead star on the far side of the galaxy reaching across the void and making its presence felt on a planet it has no direct connection to. And the flare wasn't even particularly close. If SGR 1806-20 sat where Alpha Centauri sits, 4.37 light-years away, the December 27th flare would have been the end of complex life on Earth. Not maybe, not possibly, definitely. The gamma-ray flux would have been 10 to the 8 times stronger than what we actually received. 10 to the 8, 100 million. The ozone layer would have been gone in minutes. The surface radiation dose would have spiked high enough to kill anything that wasn't buried deep underground or living at the bottom of the ocean. Even at 100 light-years, a distance that includes thousands of stars and spans a region of space large enough that most of those stars are completely invisible to the naked eye from Earth, the flare would have caused measurable damage. The ozone layer would thin, UV levels would increase, ecosystems would be stressed. Not an extinction event, but not a non-event either. Something that would show up in the fossil record as a boundary layer, a moment when a lot of species suddenly had a bad century. At 1,000 light-years, the flare would still be detectable. Satellites would register the gamma-ray spike. The magnetosphere would compress. Radio operators would notice brief disruptions. Scientists would write papers about it, but the biosphere would be fine. 1,000 light-years is far enough that the inverse square law finally does its job, and the radiation dilutes to levels that are interesting but not dangerous. SGR 1806-20 is 50 times farther than that, and it still made the news. The mechanism behind this reach is straightforward. High-energy photons don't stop. They don't slow down. They travel at the speed of light, which is the speed of causality, the fastest anything in the universe can move. Once a gamma-ray photon leaves the surface of a magnetar, it keeps going until it hits something. Most of the time, it doesn't hit anything. Space is empty. The average density of the interstellar medium is about 1 atom per cubic centimeter, sometimes less. A photon can travel for thousands of light years without interacting with a single particle. But when it does hit something, when it finally slams into an atom in a planetary atmosphere or an interstellar gas cloud, it dumps all of its energy into that interaction. A single gamma-ray photon carries millions of electron volts of energy. That's enough to ionize dozens of atoms, to break apart molecules, to kick electrons into high-energy states where they can trigger secondary reactions. Scale that up to the trillions upon trillions of photons released during a magnetar flare, and you get an event that can affect targets across galactic distances, not because the photons are magic, not because they're ignoring the inverse square law, but because the initial energy release was so absurdly large that even after diluting by a factor of 1 trillion, there are still enough photons reaching distant targets to cause measurable effects. That's the key insight. Magnetars don't cheat physics. They just operate at energy scales so extreme that physics allows them to do things that seem impossible when you're used to thinking about stars like the Sun or planets like Earth. A magnetar flare is not a normal event. It's not a scaled-up version of something familiar. It's a qualitatively different phenomenon, one that sits at the edge of what the laws of physics permit. And here's the uncomfortable part. We've only observed one flare of this magnitude. One. The December 27th event is the only time in recorded history that humans have detected a magnetar flare strong enough to affect Earth from across the galaxy. That doesn't mean it's the only time it's happened. It means it's the only time it's happened while we had instruments capable of detecting it. Magnetars have been flaring for as long as magnetars have existed. Millions of years, billions if you count the dormant ones whose magnetic fields have decayed but who were once active. Flares like December 27th probably happen somewhere in the galaxy every few decades or centuries, statistically speaking. Most of them are too far away to matter. Some of them happen in regions of the sky we're not monitoring. A few of them, over the history of Earth, have probably been close enough to cause damage. There's some evidence for this in the geological record. Certain isotope spikes in ice cores, brief periods where the concentration of beryllium-10 or chlorine-36 jumps above baseline, have been tentatively linked to cosmic ray events that don't match known supernovae or solar storms. Magnetar flares are one possible explanation. Not the only explanation, and the evidence is far from conclusive, but suggestive enough that researchers are taking it seriously. If magnetar flares have been hitting Earth periodically over the past few million years, the effects would be subtle. A brief increase in UV radiation, a temporary thinning of the ozone layer, a spike in mutation rates. Nothing that would leave an obvious mark in the fossil record, unless the flare was unusually close and unusually strong. But subtle effects compound over time. A species that's already under stress from climate change or habitat loss might not survive an additional hit from increased UV radiation. An ecosystem that's balanced on a knife edge might tip. We don't know how many magnetars are within a few thousand light years of Earth. The ones we've detected are the active ones, the ones currently flaring or emitting steady X-rays. Dormant magnetars are invisible unless they happen to be close enough that we can detect them through other means, like their gravitational influence on nearby stars or their emission of faint radio waves. The nearest known active magnetar is about 9,000 light-years away, comfortably distant, probably safe, but we don't have a complete census. There could be others, closer, waiting. And that brings us to the next question, the one that's been sitting in the background this entire time, waiting for its turn. If magnetars can reach across tens of thousands of light years and compress planetary magnetic fields with a single flare, if they can strip atmospheres from unprotected worlds and threaten biospheres at distances where most astrophysical events are harmless, then how do they compare to the other cosmic monsters we're used to worrying about? How do they stack up against black holes? Black holes have had a good run. For decades, they've held the title of scariest thing in the universe. The ultimate cosmic predator, the object so extreme that even light can't escape. The monster lurking at the center of every galaxy, waiting to devour anything that wanders too close. They've dominated popular imagination, filled documentaries, inspired 1,000 science fiction stories about ships falling through event horizons and astronauts getting spaghettified into ribbons of atoms. And they deserve the reputation. Black holes are terrifying. They warp space-time itself into knots. They erase information from the universe in ways that violate everything we thought we understood about quantum mechanics. Get too close, and you cross a boundary called the event horizon, a one-way door in space-time beyond which your future contains only one destination, the singularity at the center, a point of infinite density where the equations break down and physics as we understand it stops making sense. That's scary. That should be scary. A region of space where the escape velocity exceeds the speed of light is not a place you want to visit. Nothing, not even light, can escape once it crosses that threshold. The name itself, black hole, captures the fundamental horror. A hole in the fabric of reality, a place where things go in and never come back out. But here's the thing about black holes that doesn't get talked about enough. For all their gravitational dominance, for all the space-time warping and the event horizons and the singularities, black holes are fundamentally local threats. They don't reach out and grab you from across the galaxy. They don't emit sudden bursts of radiation that strip atmospheres off planets tens of thousands of light years away. They sit there, warping space-time in their immediate vicinity, waiting for something to wander close enough to fall in. Passive, that's the word. Black holes are passive. Don't get close and you're fine. Keep your distance. Stay outside the gravitational well. And a black hole is just a very dense object sitting in space doing what very dense objects do. It pulls. That's it. The pull is strong, yes, enormously strong. But it obeys the same inverse square law that governs every other gravitational field in the universe. Double your distance from a black hole, and the gravitational force drops to 1/4. Stay far enough away, and the black hole's influence is negligible. The nearest known black hole, as of the most recent surveys, sits about 1,500 light-years from Earth. That's close by galactic standards. There are tens of thousands of stars closer than that. Some of them are visible to the naked eye. 1,500 light-years is practically in our neighborhood, and we don't feel it at all. The gravitational pull from that black hole at Earth's distance is so weak that it doesn't affect our orbit around the Sun, doesn't perturb the trajectories of spacecraft we launch, doesn't show up in any measurement of local gravitational anomalies. The black hole is there, sitting quietly, pulling on everything around it with a force that scales exactly the way Newton's law of gravitation says it should. If you replaced that black hole with a normal star of the same mass, the gravitational effects would be identical. The only difference is that the black hole is much smaller, which means you can get much closer to all that mass before the tidal forces rip you apart. But you have to get close. That's the key. A black hole's danger zone is limited to the region near the event horizon. For a black hole with the mass of our Sun, the Schwarzschild radius, The distance from the singularity to the event horizon is about 3 kilometers. 3 kilometers. That's the size of the danger zone where crossing the boundary means you're trapped forever. Scale that up to a supermassive black hole, the kind sitting at the center of galaxies with millions or billions of times the sun's mass, and the event horizon gets bigger. A billion solar mass black hole has a Schwarzschild radius of about 3 billion kilometers, roughly 20 times the distance from the Earth to the Sun. That's a large radius, big enough that you could fit the inner solar system inside it. But it's still a local feature. It's still confined to a specific region of space. You can see it coming, you can avoid it, and outside the event horizon, even in the immediate vicinity of a black hole, space isn't fundamentally broken. It's warped, yes, severely warped. Time runs slower the closer you get to the horizon, a consequence of general relativity that's been measured and confirmed in laboratories and GPS satellites. Light bends as it passes through the warped spacetime near a black hole, creating gravitational lensing effects that distort the view of objects behind the hole. If you were somehow hovering just outside the event horizon of a solar mass black hole, you'd see the entire universe compressed into a bright ring of light above you, while below you there would be nothing. Just a circle of perfect black, the event horizon, swallowing everything that crosses it. But none of that kills you. The warping itself, the distortion of spacetime, doesn't damage matter. What kills you near a black hole is tidal forces. Gravity pulling on one part of your body harder than another part. If you fell feet first toward a solar mass black hole, your feet would be closer to the singularity than your head. The gravitational pull on your feet would be stronger, much stronger. Strong enough that the difference in force between your feet and your head would stretch you like taffy. Astronomers call this spaghettification, and it's exactly as unpleasant as it sounds. But again, this only happens if you get close. Fall toward a supermassive black hole, one with a billion solar masses, and the tidal forces at the event horizon are actually much weaker. The event horizon is farther from the singularity, and the gradient of the gravitational field is gentler. You could, in theory, cross the event horizon of a supermassive black hole and survive for a little while before the tidal forces closer to the singularity tore you apart. Not that it would matter. Once you're inside the event horizon, your fate is sealed. Every possible trajectory through spacetime leads to the singularity. You can't turn around. You can't escape. You can't even stay still, because inside the event horizon, moving toward the singularity isn't a choice. It's the structure of spacetime itself. The singularity is in your future the way tomorrow is in your future, inevitable. That's the existential horror of a black hole. Not the violence, not the tidal forces, the inevitability, the way it removes options. Outside the event horizon, you have choices. You can fire your engines, change course, escape. Inside, you don't. There's only one outcome, and no amount of thrust or clever maneuvering will change it. But that horror is confined. It exists inside a boundary. Cross the event horizon, and you're doomed. Stay outside, and you're not. The black hole doesn't reach across space and pull you in from a distance. It doesn't emit bursts of radiation that affect objects light years away. It just sits there, warping spacetime, waiting. Unless it's feeding, that's the exception. That's where black holes stop being passive and start being actively dangerous across larger distances. A black hole that's accreting matter, pulling in gas and dust from a surrounding cloud, or stripping material from a companion star in a binary system, forms an accretion disk. The infalling material doesn't plunge straight into the event horizon. It spirals inward, forming a disk of superheated gas orbiting the black hole at speeds approaching the speed of light. Friction between particles in the disk heats the gas to millions of degrees, hot enough that it radiates X-rays, hot enough that it glows brighter than entire galaxies. The accretion disk is where the real danger lives, not from the black hole itself, but from the environment the black hole creates. The disk is a furnace. Anything passing through it gets vaporized. The radiation flux near an active accretion disk is intense enough to strip electrons from atoms, ionize molecules, cook organic matter down to its constituent elements within seconds, and in some cases the black hole doesn't just pull matter in, it ejects it. Jets of particles and radiation launched from the poles of the accretion disk stream outward at nearly the speed of light. These jets can extend for thousands or even millions of light years, carving tunnels through the intergalactic medium, heating gas clouds, triggering star formation, and generally making their presence felt across vast stretches of space. If you're unlucky enough to be in the path of one of those jets, you're in trouble. The particle flux would fry any electronics, ionize any atmosphere, and deliver a radiation dose lethal to anything biological. Active galactic nuclei powered by supermassive black holes feeding on vast reservoirs of gas at the centers of galaxies can emit more energy than every star in their host galaxy combined. The jets from those black holes are visible across billions of light years. So yes, black holes can be dangerous at a distance, but only if they're feeding, only if there's an accretion disk and jets. A quiescent black hole, one that's not actively pulling in matter, is invisible. It doesn't glow, it doesn't emit jets. It's just a gravitational field sitting in space, indistinguishable from any other massive object except for the fact that it's much smaller and much denser. Most black holes are quiescent most of the time. Accretion is episodic. A black hole might go through an active phase, flare brightly for a few thousand or million years as it consumes a nearby gas cloud or tears apart a star that wandered too close, and then go quiet again for millions or billions of years as it waits for the next meal to arrive. Magnetars don't wait. They don't need to be fed. They don't need an external source of energy. They carry their own battery, stored in the geometry of their magnetic field, and they release that energy in bursts whether anything is nearby or not. A magnetar sitting alone in the middle of empty space, light years from the nearest star, can still flare, can still emit a burst of gamma rays and X-rays intense enough to light up an entire galaxy, can still reach across tens of thousands of light years and affect objects that have no direct connection to it. That's the fundamental difference. A black hole's danger is proximity dependent. A magnetar's danger is not. Let's talk about energy scales, because this is where the comparison starts to get uncomfortable for black holes. A supernova, the explosion that marks the death of a massive star and often leaves behind either a neutron star or a black hole, releases about 10 to the 53 ergs of energy. That's a 1 followed by 53 zeros. Most of that energy goes into the kinetic energy of the ejected stellar material and the neutrinos that stream out from the collapsing core. Only about 1% of the total energy, roughly 10 to the 51 ergs, comes out as visible light and other electromagnetic radiation. 10 to the 51 ergs is still an enormous number. For a few weeks, a supernova can outshine its entire host galaxy. The light is visible across millions of light years. It's one of the most energetic events in the universe, and it's a one-time thing. The star explodes, releases all that energy, and then it's over. What's left behind, the neutron star or black hole, is inert by comparison. A magnetar flare, the largest ones we've observed, releases about 10 to the 46 ergs. That's 5 orders of magnitude less than a supernova. 100,000 times less energy. On paper, it sounds like the supernova wins by a lot. But here's the catch. A supernova takes weeks to release its energy. The initial explosion happens in seconds, yes, but the visible light, the part we can detect from a distance, comes from the expanding shell of ejected material as it cools and radiates over days and weeks. The energy release is spread out over time. A magnetar flare releases its energy in a fraction of a second. The December 27, 2004 event dumped 10 to the 46 ergs into space in 0.2 of a second. The peak power output during that brief window was 10 to the 47 ergs per second. Compare that to the Sun's output, which is about 4 times 10 to the 33 ergs per second. The magnetar flare at its peak was producing roughly 25 trillion times more power than the Sun. For 0.2 of a second, that magnetar was the brightest object in the galaxy. Not one of the brightest, the brightest, outshining 400 billion stars combined. And it did this not by fusing hydrogen or accreting matter or doing anything that involves adding new energy to the system. It did it by rearranging its magnetic field, by letting the stored energy in the field geometry snap into a lower energy state and radiate the difference as gamma rays and X-rays. Now compare that to a black hole merger, the kind detected by gravitational wave observatories like LIGO, releases energy on the order of a few solar masses converted entirely into gravitational waves. Einstein's equation, E equals mc squared, tells you how much energy that is. One solar mass is about 2 times 10 to the 33 grams. The speed of light is 3 times 10 to the 10 centimeters per second. Square that and multiply by the mass, and you get about 2 times 10 to the 54 ergs per solar mass. A black hole merger that converts 3 solar masses into gravitational waves releases about 6 times 10 to the 54 ergs. That's more than a magnetar flare by 8 orders of magnitude, 100 million times more energy. But gravitational waves are different from electromagnetic radiation. Gravitational waves don't ionize atoms, they don't strip away atmospheres, they don't heat gas or break apart molecules. They're ripples in space-time itself, and they pass through matter almost completely unimpeded. A gravitational wave strong enough to be detected by LIGO causes the distance between 2 mirrors 4 kilometers apart to change by about 1,000th the diameter of a proton. Measurable with extraordinary precision, yes, but not dangerous. You could be standing right next to a LIGO detector when a gravitational wave passes through, and you wouldn't feel a thing. A magnetar flare, on the other hand, is all electromagnetic radiation, gamma rays, X-rays, photons that interact with matter, ionize atoms, heat surfaces, disrupt magnetic fields. A flare that releases 10 to the 46 ergs in the form of gamma rays is a direct threat to anything in its path. Not just detectable, dangerous. So the comparison isn't straightforward. Black hole mergers release more total energy, but in a form that doesn't directly affect matter unless you're sitting right on top of the event. Magnetar flares release less total energy, but in a form that propagates across the galaxy and can damage biospheres from tens of thousands of light years away. There's also the question of frequency. Black hole mergers are rare. LIGO detects a few dozen per year across the entire observable universe, and most of those are so far away that the gravitational waves have been traveling for billions of years before reaching us. The nearest black hole merger detected so far happened about 400 million light-years away, close by cosmological standards, but not exactly in our neighborhood. Magnetar flares, by contrast, happen in our own galaxy regularly. Every few years, somewhere in the Milky Way, a magnetar cracks its crust and releases a burst of gamma rays. Most of those flares are small, emitting 10 to the 41 or 10 to the 42 ergs. Detectable if we happen to be looking in the right direction, but not strong enough to cause any measurable effects on Earth. Every few decades, maybe every century, a large flare happens. Something in the 10 to the 46 erg range, like December 27, 2004, and those flares can be detected from across the galaxy. The statistical odds of a magnetar flare affecting Earth in any given year are low, very low. But over millions of years, over the timescales relevant to the evolution of life on this planet, the odds start to add up. If magnetars flare every few decades, and there are thousands of magnetars scattered throughout the Milky Way, some of them dormant and some of them active, then the probability that Earth has been hit by a significant magnetar flare at some point in its history is not negligible. There's no direct evidence in the geological record, no smoking gun layer of isotopes that definitively points to a magnetar flare, but absence of evidence isn't evidence of absence, and the subtlety of the effects makes it difficult to distinguish a magnetar flare from other sources of cosmic radiation like supernovae or solar storms. What we do know is that magnetar flares can affect planets from distances that would make black holes irrelevant. A black hole 1,500 light-years away is a curiosity, an object we can study with telescopes, but one that has no impact on daily life. A magnetar 1,500 light-years away is a potential threat. Not an immediate one, not something that should keep you awake at night, but a threat nonetheless. If that magnetar flared, if it released a burst of gamma rays comparable to December 27th, Earth's magnetosphere would compress, the ionosphere would light up, radio communication would stutter. Satellites might report elevated radiation levels. The ozone layer would thin slightly, recovering over months as the atmosphere re-equilibrated. Nothing catastrophic, nothing that would make headlines outside the scientific community, but measurable, real, a distant object reaching across the void and making its presence felt. A black hole at that distance does nothing unless it's actively feeding and you happen to be in the path of its jets. And even then, the jets are narrow, a few degrees wide at most. The odds of being in the beam are tiny. A magnetar flare radiates in all directions. If you're anywhere within a few thousand light years, you're in the blast zone. There's also the speed factor. Black holes, for all their space-time warping, don't send signals faster than light. Gravitational waves travel at the speed of light. If a black hole 1,500 light-years away merged with another black hole tomorrow, we wouldn't know about it for 1,500 years. The gravitational waves would take that long to reach us. A magnetar flare propagates at the speed of light too, but the effects are immediate once the photons arrive. The gamma rays hit the atmosphere and ionize it within milliseconds. The magnetosphere compresses as the charged particles created by the gamma ray cascade interact with the magnetic field. There's no delay, no gradual build-up. The flare happens, the light travels, and the moment it arrives, the effects begin. Black holes bend space-time and trap light. Magnetars don't bend spacetime in any significant way. Their gravity is strong, yes, but not strong enough to create an event horizon. The escape velocity at the surface of a neutron star is about 1/3 the speed of light. Enormous by human standards, but still below the threshold where spacetime breaks down and escape becomes impossible. What magnetars do instead is radiate. They convert stored magnetic energy into electromagnetic radiation and fling it outward at the speed of light. They don't trap anything. They release everything. And because the energy is released as photons, it spreads across the galaxy, diluting with distance but never stopping, never slowing, until it hits something. That reach, that ability to affect objects across interstellar distances without requiring proximity or accretion or any external energy source, is what makes magnetars uniquely dangerous, not more dangerous than a black hole in absolute terms. A black hole will kill you more efficiently if you get close enough, but more pervasive, more difficult to avoid, more likely to show up in your neighborhood and make itself known. Black holes dominate their immediate surroundings. Within a few Schwarzschild radii, they're the most powerful gravitational objects in the universe. Nothing escapes, nothing survives. But their influence drops off rapidly with distance, and outside the accretion disk, outside the jets, they're invisible, silent, passive. Magnetars dominate across distances. They're smaller, less massive, easier to ignore on paper, but they're active, they flare. They release energy that propagates across the galaxy and affects objects that have no business being affected by a 12-kilometer-wide star sitting tens of thousands of light-years away. The hierarchy of danger is not as simple as biggest equals most dangerous. It's not a linear scale where the object with the most mass or the strongest gravity automatically wins. Danger depends on context, on reach, on the ability to affect things that aren't immediately nearby. By that measure, magnetars are, in some ways, scarier than black holes, not because they're stronger, not because they warp spacetime more severely, but because they don't have to be close to hurt you. They can sit on the far side of the galaxy, crack their crust, release a burst of gamma rays, and 50,000 years later, that burst reaches Earth and compresses the magnetosphere. That's not something a black hole can do, and it's not something we can predict or prevent. We can map the locations of known magnetars, track their flare activity, estimate the odds of a large flare happening in any given year. But we can't stop it. We can't shield against it. We can't see it coming until the light arrives, and by then the event has already happened 50,000 years ago, and we're just now receiving the message. The universe, it turns out, has more than one way to kill you. Black holes are one method, efficient, brutal, inevitable if you cross the event horizon. Magnetars are another, quieter, subtler, but with a reach that spans the galaxy. And while we've spent decades studying black holes, mapping their properties, understanding their behavior, magnetars are still revealing surprises, still showing us that the universe's capacity for violence is not limited to the objects with the strongest gravity or the largest mass. Sometimes the scariest things are the ones that don't need to get close. The ones that can reach across the void and touch you with nothing more than light. And if that light happens to be gamma rays traveling at 300,000 kilometers per second, carrying enough energy to strip away the atmosphere of a planet, then proximity stops being the relevant variable. The question stops being how close is it and starts being how often does it flare? And we don't have a good answer to that question yet. We're still learning, still watching, still waiting for the next burst of gamma rays to light up our detectors and remind us that the galaxy is full of things we don't fully understand, things that can hurt us from distances we used to think were safe. Black holes are terrifying, but magnetars might be worse. And the worst part is, we're only just beginning to figure out how many of them are out there. We've spent 6 chapters mapping the terrain of a threat most people have never heard of. A dead star 12 kilometers wide, sitting somewhere in the galaxy, capable of reaching across tens of thousands of light years and affecting planets it has never met. A magnetic field so strong it warps atoms into needles and makes empty space behave like a material. An energy reservoir so vast that a single crack in the star's crust can release more power than the sun produces in 100,000 years. And the uncomfortable truth is, we're still at the beginning. We've observed maybe 30 magnetars in the Milky Way. We've caught one truly massive flare, the December 27, 2004 event, and a handful of smaller ones. We've built models, run simulations, written papers. We've mapped the locations of the active magnetars we can detect and estimated their magnetic field strengths and rotation periods. But the galaxy is 10 billion years old and 100,000 light-years across. Hundreds of millions of stars have exploded in that time. If even a small fraction of those explosions produced magnetars, and if magnetars stay active for tens or hundreds of thousands of years before going dormant, then the 30 we've found are just the ones shouting loud enough for us to hear. The rest are out there, quiet, invisible, waiting. And the only way we're going to find them, the only way we're going to understand what they're capable of and whether they pose any real threat to Earth or to life anywhere else in the galaxy, is to get better at looking. Better instruments, sharper eyes, new techniques that can spot a magnetar even when it's not flaring, even when it's sitting dormant in a crowded star field 50,000 light-years away, hidden behind dust and gas and the light of a million other stars. That work is already happening, and it's revealing things no one predicted. Let's start with the instruments, because the technology is where the story always begins. Magnetars were discovered, or at least first identified, as a distinct class of object, using X-ray telescopes. X-rays, photons with wavelengths shorter than ultraviolet light, and energies high enough to ionize atoms on contact, don't penetrate Earth's atmosphere. You can't study cosmic X-ray sources from the ground. You need a telescope in space, orbiting above the atmosphere, collecting photons that would otherwise be absorbed by nitrogen and oxygen molecules 100 kilometers above your head. The first generation of X-ray telescopes, satellites like NASA's Uhuru, launched in 1970, and the Einstein Observatory, launched in 1978, were designed to survey the sky and catalogue X-ray sources. They found thousands of them. Most were normal stars, binary systems where one star was pulling material off a companion and heating it to millions of degrees in an accretion disk. Some were supernova remnants, expanding shells of gas still glowing from the energy of the explosion that created them. And a few, a very small number, were soft gamma repeaters. Objects that emitted brief bursts of X-rays and gamma rays, always from the same location, on irregular timescales. Those soft gamma repeaters were the first clues, but the instruments at the time couldn't resolve enough detail to figure out what they were. The bursts were too short, the signals too weak, the technology too limited. It took decades and multiple generations of improved satellites before astronomers could pin down the rotation periods of the sources, measure their magnetic field strengths, and confirm that they were neutron stars with fields 1,000 times stronger than normal. By the 2000s, X-ray astronomy had matured. NASA's Chandra X Ray Observatory, launched in 1999, and ESA's XMM Newton, launched the same year, brought unprecedented resolution and sensitivity. These were not survey instruments, they were precision tools, capable of studying individual objects in exquisite detail. Point Chandra at a magnetar, and it could measure the spectrum of the emitted X-rays, trace how the brightness changed over time, detect oscillations in the light curve that revealed the star's internal structure. Chandra and XMM Newton are still operating today, more than 2 decades after launch, and they're still producing new results, but they have limitations. X-ray telescopes can tell you that a magnetar is there, that it's emitting radiation at a certain energy, that it's rotating at a certain speed. What they can't tell you is the geometry of the magnetic field itself. The shape, the structure, the way the field lines twist and loop and tangle in the star's magnetosphere. For that, you need polarization measurements. Light is a wave, an oscillating electric and magnetic field propagating through space. Normally, the oscillations are random. The electric field wiggles in all directions perpendicular to the direction the light is traveling. That's unpolarized light. But certain processes can align those oscillations, forcing the electric field to wiggle in a specific direction. That's polarized light. And by measuring the polarization, the direction and degree to which the light is aligned, you can learn about the environment that produced it. Magnetic fields polarize light strongly. If light is emitted in the presence of a powerful magnetic field, the field forces the photons to align their electric field oscillations parallel or perpendicular to the field lines. The degree of polarization and the orientation of the polarization axis give you a direct probe of the magnetic field geometry. It's like being handed a map of the field without having to guess at its structure from indirect measurements. For decades, astronomers wanted to measure the polarization of X-rays from magnetars. The problem was that X-ray polarization is incredibly difficult to detect. The photons are high energy, which means their wavelengths are tiny, on the order of a nanometer or less. Building a detector that can measure the polarization of something with a wavelength that's small, without losing all the photons to noise or scattering, is a serious engineering challenge. In December 2021, NASA launched the Imaging X-ray Polarimetry Explorer, IXPE for short. It's a small satellite about the size of a refrigerator, carrying 3 identical telescopes equipped with polarization-sensitive detectors. The mission was designed specifically to measure the polarization of X-rays from a variety of cosmic sources: pulsars, supernova remnants, active galactic nuclei, and magnetars. IXPE's observations of magnetars have been revelatory. In 2022, the satellite pointed at a magnetar called 4U0142+61, a well-studied object sitting about 13,000 light-years away in the constellation Cassiopeia. The polarization measurements revealed that the X-rays coming from the star were highly polarized, with the polarization axis aligned almost perfectly with the star's rotation axis. That alignment told researchers that the emission was coming from regions near the magnetic poles, where the field lines are strongest and most tightly packed. But the degree of polarization was lower than some models predicted. Theoretical calculations suggested that X-rays emitted in a field as strong as a magnetar's should be almost 100% polarized. IXPE measured about 80%. That 20% gap is significant. It suggests that something in the magnetosphere, some process involving scattering or re-emission of photons, is randomizing the polarization slightly. The leading candidate is resonant cyclotron scattering, a quantum mechanical effect where photons interact with electrons, spiraling along magnetic field lines, and get their polarization angles shifted in the process. This is exactly the kind of detail that separates a rough understanding from a precise one. The models predicted high polarization. IXPE measured slightly less. Now theorists have to go back and refine their calculations, add in the scattering processes they might have underestimated, and see if the updated models match the data. It's an iterative process, the way science always works. Predict, measure, adjust, repeat. IXPE has also observed other magnetars and found that the polarization varies depending on the energy of the X-rays. Lower energy photons are polarized differently than higher energy ones, which suggests that they're being emitted from different regions of the magnetosphere or undergoing different amounts of scattering before escaping. That spatial and spectral information is feeding into three-dimensional models of magnetar magnetospheres, giving researchers a much clearer picture of how the magnetic field geometry affects the emitted radiation. And this is just the beginning. IXPE is a Pathfinder mission, a proof of concept. It's shown that X-ray polarimetry works, that it can deliver scientifically useful measurements, and that the technique is mature enough to justify building bigger, more sensitive instruments. The next generation of X-ray polarimeters, currently in the planning stages at NASA and ESA, will have larger collecting areas and finer angular resolution. They'll be able to map the polarization of magnetar emission across the star's surface, tracing how the field geometry changes from the poles to the equator. That level of detail will let researchers test models of neutron star crusts, the solid outer layer of the star where the magnetic field is anchored. The crust is where the starquakes happen, where the stress builds up and the field lines twist and eventually snap. Understanding the structure and composition of the crust is key to understanding why magnetars flare and how often those flares should occur. Current models suggest the crust is made of iron nuclei arranged in a crystalline lattice, held together by electromagnetic forces and compressed to densities 1 billion times higher than lead. But the exact properties of that lattice, how it responds to magnetic stress, how it cracks under strain, are still uncertain. Laboratory experiments can't help here. You can't build a chunk of neutron star crust in a lab. The pressures and densities are too extreme. The only way to test the models is to observe real neutron stars and see how they behave. Magnetars, with their frequent flares and measurable oscillations, are the best laboratory available. Then there's the question of what's happening below the crust. The interior of a neutron star is still largely theoretical. We know the outer crust is solid, a crystalline lattice of nuclei. Below that, the inner crust is thought to be a mixture of nuclei and free neutrons, a kind of nuclear pasta where the matter clumps into strange shapes, rods and sheets and bubbles, depending on the density and pressure. Deeper still, the core is probably a superfluid, a state of matter where neutrons flow without friction, their quantum mechanical wave functions overlapping to create a macroscopic fluid that behaves like nothing on Earth. And if the density gets high enough, if the pressure at the very center of the neutron star exceeds a certain threshold, the neutrons themselves might break apart into their constituent quarks. Nobody knows for sure. The equation of state, the relationship between pressure and density at those extremes, is uncertain. Different models predict different outcomes. Some say the core stays as neutrons all the way down. Others say there's a quark core at the center, a region where the fundamental building blocks of protons and neutrons exist freely instead of being confined inside particles. Magnetars probe this regime. Their oscillations, the ringing that happens after a large flare, depend on the structure of the interior. Different modes of vibration correspond to different internal compositions. By measuring the frequencies of those oscillations and comparing them to theoretical predictions, researchers can constrain the equation of state. It's an indirect measurement, yes, but it's one of the only ways we have to study matter under conditions that can't be replicated anywhere else. This ties into one of the broader implications of magnetar research. These objects are not just interesting for their own sake. They're testing grounds for fundamental physics. The magnetic fields are strong enough that quantum electrodynamics, the theory governing how light and matter interact, makes predictions that have never been tested in any laboratory. Vacuum birefringence, the splitting of light into two polarizations as it passes through a magnetized vacuum, was predicted in the 1930s and first observed definitively near a magnetar in 2017. That observation confirmed a prediction that had sat in textbooks for 80 years with no way to test it. Magnetars might also be connected to some of the most mysterious phenomena in modern astronomy. Fast radio bursts. Fast radio bursts, FRBs for short, are brief flashes of radio waves lasting only a few milliseconds that arrive at Earth from distant galaxies. They were first discovered in 2007 when an astronomer named Duncan Lorimer was digging through archival data from the Parkes Radio Telescope in Australia. He found a signal that was ridiculously bright, ridiculously short, and ridiculously distant. The burst had traveled billions of light-years before reaching Earth, which meant the source had to be extraordinarily energetic to be detectable at that range. For years, FRBs were a mystery. They repeated unpredictably. They came from all over the sky. They didn't match any known astrophysical source. Dozens of theories were proposed. Collapsing stars, merging black holes, evaporating primordial black holes, alien civilizations, you name it. The field was wide open, and every new detection just made the picture more confusing. Then, in April 2020, a fast radio burst was detected coming from inside the Milky Way, not billions of light-years away, 30,000 light-years, close enough that astronomers could pinpoint the exact location, and the source was a magnetar. The magnetar in question, SGR 1935 plus 2154, had been known for years as a soft gamma repeater. It flared occasionally, emitted X-rays, behaved like a typical magnetar. On April 28, 2020, it produced a burst of radio waves that matched the profile of an FRB. Milliseconds long, extraordinarily bright, energetic enough that if it had come from a galaxy a billion light-years away, it would have looked exactly like the extragalactic FRBs astronomers had been puzzling over for more than a decade. That detection changed everything. It didn't prove that all FRBs come from magnetars, but it showed that magnetars are capable of producing FRB-like signals. And since magnetars are relatively common, at least compared to things like merging black holes or exploding primordial singularities, they became the leading candidate for the source of at least some FRBs. The mechanism is still being worked out. The prevailing model involves starquakes, the same kind of crust-cracking events that trigger large flares. When the crust shifts, the magnetic field lines anchored in the crust snap and reconnect. That releases energy in the form of gamma rays and X-rays, which we've observed many times. But under certain conditions, the reconnection can also accelerate particles to extremely high energies, creating a relativistic shock wave that propagates outward through the magnetar's magnetosphere. That shock wave, as it plows through the surrounding plasma, can generate coherent radio emission. A brief, intense pulse of radio waves traveling outward at the speed of light. If the geometry is right, if the shockwave is aimed toward Earth, we see it as a fast radio burst. If it's aimed somewhere else, we don't. That explains why FRBs are rare. Not because the sources are rare, but because the emission is beamed. Most magnetar flares don't produce detectable radio bursts because the emission is pointed in the wrong direction. Every once in a while, though, the geometry lines up and we catch one. The link between magnetars and FRBs is not settled yet. Some researchers are fully convinced. Others are cautious, pointing out that not all FRBs have the same properties and that there might be multiple types of sources producing similar signals. But the April 2020 detection was a major piece of evidence. It's hard to argue with a fast radio burst that came from a known magnetar during a period when that magnetar was actively flaring. If magnetars are responsible for at least some FRBs, and if FRBs are as common as current surveys suggest, then there are a lot more magnetars out there than we've detected. The extragalactic FRBs we're seeing come from distances of hundreds of millions or billions of light-years. We can't resolve individual stars at those distances. We can barely resolve individual galaxies. But the bursts are bright enough to be detected across that span, which means the sources have to be producing enormous amounts of energy in a very short time. Magnetars fit the bill. They're the only known objects that can generate that much power in milliseconds without being supernova or gamma-ray bursts, which have different observational signatures. If every galaxy has a population of magnetars similar to the Milky Way's, and if even a small fraction of those magnetars are actively flaring, then the rate at which FRBs should be detected matches what we're actually seeing. The numbers line up, and that raises an unsettling possibility. If magnetars are common enough and active enough to explain FRBs across the entire observable universe, then they're also common enough that one could be sitting relatively close to Earth, dormant, undetected, waiting for the right trigger to crack its crust and flare. We've mapped the 30 or so active magnetars in the Milky Way. We've tracked their flare activity, measured their rotation periods, estimated their ages, but the dormant ones are invisible. A magnetar that's been quiet for a few 100,000 years, its magnetic field, decayed below the threshold where it flares regularly, doesn't emit much X-ray radiation. It's just a hot, dense lump of neutrons spinning in space. No accretion disk, no bright jets. Nothing to make it stand out. You could find it if you got close enough. The star still has a gravitational field. It still emits faint thermal radiation as it cools, but at a distance of a few thousand light-years, surrounded by the light of millions of other stars and hidden behind clouds of dust and gas, a dormant magnetar is effectively invisible. Some estimates suggest there could be tens of millions of dormant magnetars in the Milky Way. That number comes from extrapolating the supernova rate over the galaxy's lifetime and assuming a small fraction of those supernovae produce magnetars. If 1 in 10 supernovae leaves behind a magnetar, and if the Milky Way has seen a few 100 million supernovae, then there should be tens of millions of magnetars scattered throughout the galaxy right now. Most of them dead, quiet, no longer active, but a fraction still young enough, still carrying enough stored magnetic energy that they could flare again. We have no way to survey them all. No instrument currently in operation or even on the drawing board can detect a dormant magnetar unless it happens to be very close or unless it flares while we're watching. The galaxy is too big, the stars too numerous, the signals too faint, but the tools are improving. Radio surveys like the Canadian Hydrogen Intensity Mapping Experiment CHIME and the Square Kilometre Array, currently under construction, are designed to detect transient radio sources across the entire sky. They're sensitive enough to catch fast radio bursts from billions of light-years away, which means they're also sensitive enough to catch weaker bursts from magnetars within the Milky Way. If a dormant magnetar flares and produces a radio burst, CHIME or SCAR will see it. And once they see it, follow-up observations with X-ray telescopes can confirm the source and add it to the catalogue. Over the next decade, as these surveys come online and start accumulating data, the number of known magnetars will probably increase. Maybe not by a factor of 10, but by enough that the statistical picture becomes clearer. We'll have a better sense of how common they are, how often they flare, how long they stay active before going quiet. And that data will feed back into the models, refining our understanding of how magnetars form, why their magnetic fields are so strong, and what determines whether a given neutron star becomes a magnetar or a normal pulsar. Theoretical work is moving in parallel. Magnetohydrodynamic simulations, computer models that solve the equations governing how magnetic fields interact with conducting fluids, are being run on some of the most powerful supercomputers in the world. These simulations start with a newborn neutron star, a hot, rapidly rotating ball of neutrons and protons and electrons, and they follow the evolution of the magnetic field over thousands of years. The simulations show how convection currents in the star's outer layers can twist and amplify the field, how the field lines can tangle and store energy, and how the crust can crack under magnetic stress. The level of detail is improving every year. Early simulations run in the 2000s were limited to 2 dimensions. They could model how the field evolved in a plane, but couldn't capture the full 3-dimensional complexity of the star's interior. Modern simulations are fully 3-dimensional, tracking the field in all 3 spatial dimensions and resolving features down to scales of a few meters. That resolution is important because the star quakes, the cracks in the crust that trigger flares, propagate on those small scales. A fracture, a few millimeters wide, can circle the entire star and release enough energy to light up a galaxy. Capturing that process in a simulation requires enormous computational power and very fine spatial grids. The simulations are also incorporating more realistic physics. Early models treated the neutron star crust as a simple elastic solid, like a chunk of steel. But the crust of a neutron star is not a normal material. It's a lattice of iron nuclei compressed to densities where the nuclei are almost touching, held together by quantum mechanical effects that don't have analogues in everyday experience. The crust can flow under stress, a process called plastic deformation, where the lattice rearranges itself without breaking. It can also fracture suddenly, like glass, if the stress exceeds a critical threshold, and the presence of a superfluid layer just below the crust complicates things further because the superfluid doesn't rotate with the crust. It decouples, spinning at a different rate, and the friction at the boundary between the crust and the superfluid can transfer angular momentum back and forth, driving changes in the star's rotation period. All of these effects are being added to the models, one piece at a time, as researchers figure out how to calculate them and as the computational power becomes available to run the simulations. The goal is to build a complete, self-consistent picture of a magnetar's interior from the surface down to the core, that can predict when and how the star will flare based on its rotation history, its magnetic field configuration, and its thermal evolution as it cools. We're not there yet. The models are good, but they're not perfect. They can reproduce some observed features, like the decay timescales of flares and the oscillation frequencies of the star's crust after a quake, but they still struggle to predict the exact energy release of a flare or the intervals between flares. There's too much uncertainty in the initial conditions, too much chaos in the way the magnetic field evolves for the models to make precise predictions. But that's okay. Precision isn't the goal yet. Understanding is, and the models are giving us that. They're showing us how a magnetar works, how the different pieces fit together, how the magnetic field drives the dynamics of the crust and the magnetosphere. They're also revealing new phenomena that weren't anticipated. One recent simulation found that under certain conditions, the magnetic field inside a magnetar can undergo a sudden large-scale rearrangement, a kind of magnetic avalanche where field lines throughout the star snap and reconnect simultaneously. That process would release an enormous amount of energy, far more than a typical flare, possibly explaining the rare hyperflares like the December 27, 2004 event. If magnetic avalanches are real, and if they can happen unpredictably when the field reaches a certain level of twist and complexity, then magnetars might be capable of even larger outbursts than we've observed so far. The December 27th flare released 10 to the 46 ergs. A full-scale magnetic avalanche could release 10 to the 47 or even 10 to the 48 ergs. That's 10 times to 100 times more energy. An event like that, from a magnetar a few thousand light-years away, would not just thin the ozone layer, it would obliterate it, and the biosphere would pay the price. We don't know if such events happen, we've never observed one. but the simulations suggest they're possible, and if they're possible, then the threat posed by magnetars is larger than the current data indicates. The broader implications extend beyond magnetars themselves. Neutron stars in general, and magnetars in particular, are laboratories for physics that can't be studied anywhere else. The densities exceed anything achievable in particle accelerators. The magnetic fields exceed anything achievable in laboratories by factors of billions. The temperatures and pressures probe regimes where quantum mechanics, general relativity, and nuclear physics all intersect in ways that are still not fully understood. One of the big unsolved problems in physics is the equation of state for nuclear matter at supranuclear densities. What happens to protons and neutrons when you squeeze them together harder than they're squeezed inside atomic nuclei? Do they stay as protons and neutrons, or do they break apart into quarks? And if they break apart, do the quarks form a new kind of fluid, a quark-gluon plasma, or a color superconductor, with properties unlike anything we've seen? Neutron star observations are the best way to answer those questions. By measuring the masses and radii of neutron stars, and by studying how they respond to perturbations like starquakes and tidal forces in binary systems, researchers can constrain the equation of state. Different equations of state predict different relationships between mass and radius. A stiffer equation of state, where the matter resists compression more strongly, predicts larger radii for a given mass. A softer equation of state predicts smaller radii. Magnetars add another layer to this, because their magnetic fields are so strong that they affect the structure of the star. The magnetic pressure can deform the shape, making the star slightly oblate, squashed at the poles, and bulging at the equator. That deformation changes the moment of inertia, which changes the rotation rate, which shows up in the timing observations. By measuring how a magnetar's rotation changes over time and comparing it to models that include magnetic pressure, researchers can learn about the interplay between magnetic fields and nuclear matter at extreme densities. This is not abstract. The data from these observations feeds into models of neutron star mergers, the collisions between two neutron stars that produce gravitational waves and short gamma-ray bursts. Those mergers are where the heaviest elements in the universe, things like gold and platinum and uranium, are created. Understanding the equation of state helps predict how much material gets ejected during a merger and what elements that material contains. That in turn helps explain the chemical evolution of the galaxy and why Earth has the particular mix of elements it does. So magnetar research is not just about understanding magnetars, it's about understanding the universe, how stars die, how matter behaves under extremes, how magnetic fields shape the cosmos, how the elements that make up planets and life are forged in the most violent events nature can produce. And there's still so much we don't know. We don't know why some neutron stars become magnetars and others don't. We don't know how long a magnetar stays active before its field decays and it goes quiet. We don't know whether all FRBs come from magnetars or whether there are other sources we haven't identified yet. We don't know if there are undiscovered magnetar phenomena, exotic modes of behavior that only show up under specific conditions we haven't observed. One possibility that's been discussed is whether magnetars can produce gravitational waves. Normal neutron stars are nearly perfect spheres. Any deviation from sphericity, any lump or bulge on the surface, would generate gravitational waves as the star rotates. But those deviations have to be tiny, fractions of a millimeter, for a neutron star to produce detectable gravitational waves over the long timescales that current detectors can observe. Magnetars, with their strong magnetic fields deforming the crust, might have larger deviations, The magnetic pressure could create a permanent bulge, a mountain on the star's surface that sticks out by a few centimeters. That's enormous by neutron star standards. A centimeter-scale deformation on a 12-kilometer object is a significant asymmetry, and as the star rotates, that bulge would generate gravitational waves. The waves would be weak, much weaker than the gravitational waves from black hole or neutron star mergers, but they'd be continuous, emitted steadily as long as the star is rotating and the bulge exists. Current gravitational wave detectors like LIGO and Virgo are not sensitive enough to detect those signals from most magnetars, but future detectors with better sensitivity and longer observation times might be. If we could detect gravitational waves from a magnetar, we'd have a direct probe of the star's interior structure. The frequency and amplitude of the waves depend on the size and location of the deformation, which depends on how the crust responds to magnetic stress. That information would complement the X-ray and radio observations, giving us a multi-messenger view of the star. Light tells you what's happening on the surface and in the magnetosphere. Gravitational waves tell you what's happening deep inside. That's the future of magnetar research. More instruments, more detectors, more wavelengths, more messengers, building a complete picture of these objects by attacking the problem from every angle available. X-rays, radio waves, gamma rays, gravitational waves, polarization, timing, spectroscopy. Each technique reveals a different piece of the puzzle, and as the pieces accumulate, the picture becomes clearer, but it will never be complete. There will always be uncertainties, always phenomena we didn't predict, always surprises lurking in the data. That's the nature of studying objects at the edge of what physics allows. Magnetars push every boundary. Density, magnetic field strength, energy release, rotation rate. They sit at the intersection of so many extreme regimes that predicting their behavior requires physics we're still developing. And that's what makes them so compelling. They're not just dangerous. They're not just exotic. They're windows into realms of nature we can't access any other way. Every observation, every flare, every burst of gamma rays or radio waves or gravitational waves is a gift. A message from the universe telling us what happens when you compress matter to the breaking point and wrap it in a magnetic field strong enough to tear atoms apart. We've spent decades building the tools to listen to those messages. IXPE is listening, Xiaomi is listening, LIGO is listening, and in the next decade, a new generation of instruments will come online, sharper and more sensitive than anything before. The square-kilometer array will survey the sky for transient radio sources with unprecedented coverage. The Einstein telescope, a proposed third-generation gravitational wave detector, will push sensitivity down to the point where continuous waves from rotating neutron stars might become detectable. The next generation of X-ray polarimeters will map Magnetars magnetospheres in 3 dimensions, tracing the geometry of the strongest magnetic fields in the universe. And somewhere out there, tens of thousands of light-years away, a magnetar is cracking its crust. The light from that flare is already on its way. It left the star before humans learned to write, before we built cities, before we looked up at the sky and wondered what those lights were. It's been traveling across the galaxy for millennia, spreading out, diluting, but never stopping, never slowing. And one day, maybe tomorrow, maybe 1,000 years from now, those photons will arrive. They'll hit our detectors, compress our magnetosphere, ionize our atmosphere, and we'll add another data point to the catalogue, another piece of the puzzle, another reminder that the universe is full of things that can hurt us from distances we used to think were safe. The nearest known magnetar is 9,000 light-years away, probably safe, probably far enough that even a massive flare wouldn't pose a direct threat to the biosphere, but probably is not the same as certainly. and we don't have a complete census of every neutron star within 10,000 light-years. We're missing data, we're missing objects. And until we map them all, until we know where every magnetar is and what it's doing, there's a gap in our knowledge, a blind spot. And in that blind spot, somewhere in the dark, a dead star might be waiting. 12 kilometers wide, spinning once every few seconds, carrying a magnetic field 1 quadrillion times stronger than Earth's. A field so intense that it warps atoms and polarizes the vacuum and stores enough energy to light up a galaxy. A field that sooner or later is going to snap, and when it does, the universe will send us a message, written in gamma rays, traveling at the speed of light, crossing the void in a journey that takes longer than civilizations last, and we'll receive it, whether we're ready or not. That's the future of magnetar research, not just understanding, watching, waiting, listening to the universe's most dangerous objects as they crack and flare and shout across the galactic dark, and hoping quietly that none of them are close enough to matter, because if one is, we won't know until the light arrives, and by then the event will already be 50,000 years in the past, already done, already decided, and all we'll be able to do is measure the damage and write it down. The universe, it turns out, has a long memory, and magnetars are the loudest voices in it. We started with a dead star, 12 kilometers wide, mass greater than the sun, spinning quietly in the dark, holding a magnetic field so strong it breaks the rules we thought governed how matter and energy behave. And somewhere in that description, black holes stopped being the scariest thing in the room, because a black hole, for all its existential weight, plays by predictable rules. Stay outside the event horizon and you're safe. Gravity follows an inverse square law. The danger is local, confined, avoidable if you know where the boundary sits. A black hole doesn't reach, it pulls, and only if you're close enough to let it. Magnetars don't wait for you to get close. They reach across the galaxy. They send bursts of gamma rays traveling for 50,000 years, crossing distances so vast that entire civilizations rise and fall in the time it takes the light to arrive. And when it does arrive, when those photons finally complete their journey and slam into a planetary atmosphere, they don't ask permission. They compress magnetospheres. They strip ozone. They ionize matter that had no idea a star died halfway across the Milky Way before humans even existed. That's not a normal threat. That's not something you can see coming or prepare for or avoid by staying far enough away. That's the universe demonstrating that distance is not the same as safety. That a dead star with no fuel, no accretion disk, no active energy source can still be the most dangerous object within 10,000 light-years simply by virtue of what it is, a wound in space-time that hasn't finished bleeding. And the worst part, the part that sits wrong no matter how many times you run the numbers, is that we don't know how many of them are out there. 30 confirmed, thousands suspected, tens of millions dormant, invisible, waiting, and any one of them could crack tomorrow, could flare, could send a message written in gamma rays that won't reach us until long after everyone alive today is dust. The light is already on its way, somewhere, from some magnetar we haven't found yet. And when it arrives, it won't matter that we didn't see it coming. The universe doesn't care about fairness. It cares about physics, and the physics say that a magnetic field